Imagine a colossal, invisible force in the heart of the galaxy that controls its existence. This hidden conductor is none other than a supermassive black hole. Although often represented as chaotic monsters that devour everything, these giants play a vital role in the life cycle of galaxies. In the center of most large galaxies is a supermassive black hole whose gravitational force is so strong that not even light can escape it. However, they actually do much more than absorb matter. They act as the heart and lungs of their galaxies, breathing life into the celestial environment in ways we are only beginning to understand. Recent research shows that the jets of gas and radiation expelled from the poles of supermassive black holes are similar to the airwaves that feed our lungs. These jets create shock waves that oscillate in a manner very similar to the thoracic diaphragm of our chest cavity, which moves to inflate and deflate lungs. This respiratory system helps regulate the growth of galaxies, preventing them from becoming too large and ensuring a delicate balance in the cosmic ecosystem. A simulation shows how the heart and lungs of a galaxy, in the form of gas columns from a central supermassive black hole, can prolong its life. If these supermassive black holes did not act as galactic regulators, the universe would be full of zombie galaxies, huge clusters of dead or dying stars. The shock waves generated by the jets of black holes can prevent star formation by heating the surrounding gas and preventing it from cooling and condensing to form new stars. This process may seem destructive, but it is necessary to maintain the health and longevity of galaxies. Today we will try to understand the mysterious nature of supermassive black holes. We will learn the profound impact they have on the universe, and, in the end, realize that even in the darkest corners of the cosmos, there's a heartbeat that connects us all. To fully understand the impact of black holes on galaxies, we need to understand their formation, their types, and some key discoveries. Black holes can form in two main ways. The most common way is associated with the death of massive stars. When a star with a mass between 8 and 10 times that of our Sun exhausts its nuclear fuel, a catastrophic explosion known as a supernova occurs. The core collapses under its own gravity, forming a stellar black hole. These black holes usually have a mass several times greater than the Sun's. Another way is through the direct collapse of massive gas clouds, which completely omits the stage of star formation. This process can lead to the formation of black holes with masses ranging from thousands to hundreds of thousands of solar masses. These direct collapses are believed to have occurred in the early universe and were the origin of the supermassive black holes we see today. The concept of black holes was first predicted by Carl Schwarzschild in 1915 as an exact solution to Einstein's equations of general relativity. These equations describe how matter shapes the fabric of space and time. Schwarzschild's solution allowed us to discover regions where gravity is so strong that nothing, not even light, can escape. The first black hole confirmed by observations was Cygnus X-1, discovered in 1964. This stellar mass black hole in the Milky Way was identified by the emission of X-rays caused by material accretion from a companion star. This discovery was the first compelling evidence that black holes are not just theoretical constructs, but real objects in the universe. Scientists have determined that a black hole consists of three main regions: the event horizon, the photon sphere, and the singularity. The event horizon is the limit beyond which nothing can pass. Once inside its limits, the photon sphere is a region where gravity is so strong that light particles are forced to orbit the center. There's a singularity, a point of infinite density, where the laws of physics, as we know them, break down. Black holes come in various sizes. Stellar mass black holes form from the collapse of stars and have masses several times greater than that of the Sun's supermassive black holes, located in the center of most galaxies, have masses ranging from millions to billions of solar masses. Intermediate mass black holes, less common, fall between these two categories and have masses between 100 and 100,000 solar masses. The 2019 Event Horizon Telescope collaboration captured the first image of a black hole located in the M87 galaxy. In this historic image, the shadow of the black hole can be seen against a bright accretion disk. The observation provided direct visual confirmation of theories about black holes and opened new possibilities for studying these mysterious objects. One of the most common and debated questions lately about black holes is whether they die. According to Stephen Hawking's theory, black holes can slowly evaporate over time through a process known as Hawking radiation. This occurs when pairs of virtual particles form near the event horizon. One falls into the black hole, and the other flies away for an incredibly long period. This trickle of ejected particles can cause the black hole to lose mass and eventually vaporize. Although black holes are depicted in science fiction, they are not cosmic vacuum cleaners that indiscriminately absorb everything around them. Objects must get incredibly close to the event horizon. Furthermore, although it has been proposed that black holes could be wormholes or portals to other universes, these ideas remain speculative and are not supported by observational data. Scientists estimate that the Milky Way alone contains more than 100 million black holes. Understanding the fundamentals of black holes, how they form, their different types, and key discoveries, lays a solid foundation for studying their profound impact on galaxies and the entire universe. So, although supermassive black holes are invisible, their presence is noticeable due to the enormous gravitational forces they exert on their environment. But how do these colossal formations arise, and what are their defining characteristics? In theory, a black hole forms when a significant amount of matter is compressed into an incredibly small space, creating a gravitational field so powerful that nothing can escape. This concept, previously considered too fanciful to be real, is now an accepted reality. Black holes, especially supermassive ones, are scattered throughout the universe, and their number may amount to billions. Supermassive black holes, with masses millions or billions of times greater than the Sun, are detected by their gravitational influence on nearby stars. These stars orbit the black hole much faster than they would around a normal object of similar mass. By measuring these orbital speeds, astronomers can estimate the black hole's mass. For example, the black hole located in the center of our Milky Way, Sagittarius A, has a mass of about 4 million solar masses. Some supermassive black holes even exceed Sagittarius A. The dwarf galaxy Leo 1 houses a black hole with a mass of about 3 million solar masses. In the neighboring elliptical galaxy Centaurus A, there's another black hole with an astonishing mass of 55 million solar masses, and even more colossal is a black hole in the galaxy cluster 2261, whose mass is estimated at about 100,000 million solar masses, although its exact location remains undetermined. Specify. These black holes, especially in active galaxies, behave differently, surrounded by an accretion disk of gas and dust that rotates rapidly and can emit enormous amounts of energy, sometimes eclipsing their entire galaxy. This same process was famously captured by the Event Horizon Telescope in 2019, when it photographed the accretion disk around the supermassive black hole in Messier 87, revealing the ominous shadow of a black hole with a mass of 6,500 million solar masses. The formation of these supermassive black holes is a subject of intense study and speculation. Unlike the vacuum cleaners in science fiction stories, real black holes attract matter by gravity, not by active suction. This gravitational attraction becomes unusually strong at short distances, but at greater distances, it behaves like the attraction of any other object of similar mass. According to one theory, the oldest supermassive black holes formed almost immediately by the gravitational collapse of massive gas clouds containing as much matter as millions of stars. This direct collapse model suggests that these black holes could have formed in as few as 150 million years, a blink of an eye by cosmic standards. According to another hypothesis, primordial black holes, born in the extreme conditions of the Big Bang, served as seeds for later growth. By studying these colossal formations, we obtain information about the fundamental processes that shape galaxies and, by extension, the universe itself. But what happens when two galaxies collide? It is not just a dramatic cosmic event. It is a transformative process that changes the very structure of the universe. At the center of these galactic collisions are supermassive black holes, and their interactions produce some of the most energetic phenomena known. When galaxies approach each other, their central supermassive black holes begin to interact gravitationally, spiraling toward an inevitable fusion. This process is not silent, but sets in motion enormous amounts of ambient gas and dust, creating a turbulent environment conducive to extraordinary phenomena. Physicists have modeled these colossal mergers and discovered that, as black holes spiral closer, they can produce jets of incredibly energetic electromagnetic radiation that shoot out along the axis of rotation with much more power than those normally observed around isolated black holes. The cosmic spectacle begins even before the black holes completely merge, offering astronomers a possible warning of these events. When these supermassive black holes finally collide, their jets combine into a single high-energy burst that may be accompanied by less directional bursts, increasing the chances of detection. The fusion process sets the surrounding plasma in motion, causing powerful jets that, in theory, can be observed from billions of light-years away. The detection of these cosmic events is not only exciting, but offers a unique opportunity to test the limits of Einstein's general theory of relativity under extreme conditions. The observation of these mergers can reinforce the current understanding of gravity or open new avenues in physics, which could lead to alternative theories. Future missions, such as the Laser Interferometer Space Antenna, or simply LISA, promise to expand our ability to locate these mergers. LISA, a joint project of NASA and the European Space Agency, will orbit the Sun and detect the gravitational waves emitted by these mergers. The combination of gravitational wave data with electromagnetic observations will allow these energetic events to be precisely located and studied in detail. Until these advanced instruments are operational, astronomers rely on existing observatories to detect electromagnetic jets. These provide a dynamic view of the evolution of galaxies, demonstrating how these mergers can drastically change the structure and behavior of galaxies. But let's take a closer look at Sagittarius A, which has 43 million times the mass of the Sun. In mid-spring of this year, our galaxy's giant revealed new secrets thanks to advanced observations from the Event Horizon Telescope. For the first time, astronomers have recorded polarized light around Sagittarius A, providing new insights into the magnetic fields surrounding this black hole. Polarized light is crucial for understanding these fields, as it shows how light waves are oriented and allows us to understand the properties of the gas and the mechanisms that drive the black hole. Interestingly, the magnetic fields around Sagittarius A are surprisingly similar to those observed around the much larger black hole in the galaxy Messier 87, which has a mass of 65 billion times that of our Sun. This similarity suggests that strong and organized magnetic fields may be a common feature of all black holes, regardless of their size. The presence of such magnetic fields makes the possibility that Sagittarius may contain a hidden jet intriguing. In other black holes, these fields drive powerful currents of matter, although Sagittarius A appears relatively calm and consumes a minimal amount of matter. The similar structure of its magnetic field points to the possibility of a weak jet that has not yet been observed. This new image of the black hole in the center of the Milky Way tells us that there are strong rotating and ordered magnetic fields near the black hole, explains Sarah Issoun, co-director of the study and fellow of the NASA Hubble-Einstein program at the Center for Astrophysics of Harvard and Smithsonian. These fields are crucial to how black holes interact with the gas and matter around them. It was the EHD, a set of telescopes around the world, that made these revolutionary observations possible by combining data from multiple telescopes. The EHD forms a virtual telescope the size of the Earth, capable of capturing unprecedented details of black holes. Although Sagittarius A is closer, it presents a unique challenge due to its smaller size. The material that rotates around it moves quickly, making it difficult to obtain sharp images. On the contrary, in the larger M87, The material moves slowly, which facilitates observation. Overcoming these difficulties has provided data to compare black holes at opposite ends of the mass range. The observed similarity in the magnetic fields between Sagittarius A and Messier 887 suggests that our galaxy's central black hole could have a hidden jet. If it existed, it would provide new knowledge about the behavior and evolution of black holes and the galaxies where they are located. The observation of this jet would be a great advance, relating Sagittarius A to the energetic processes that form galaxies. The discovery of this jet would greatly expand our understanding of how black holes affect their environments. Jets can expel gas and dust, which affects star formation and the overall evolution of galaxies. By comparing different black holes, astronomers can identify the universal principles that govern these mysterious objects. The study of our supermassive black hole allows us to root these abstract concepts in a familiar context, bringing distant space closer to home. The influence of supermassive black holes extends well beyond their gravitational effects. Relativistic jets can have a dramatic effect on the formation and evolution of galaxies, affecting everything from star formation to the distribution of gas and dust. A striking example of the influence of black hole jets is the Teacup Galaxy, located at a distance of about 1,300 million light-years from Earth. The Teacup Galaxy owes its name to its peculiar handle shape, which was formed due to the activity of a relativistic jet from its central supermassive black hole. This galaxy is a clear example of how even low-power jets can significantly affect the environment, even in radio-silent galaxies. Jets can redistribute and disrupt the surrounding gas, which will have an impact on the galaxy's ability. Recent observations with the Atacama Large Millimeter Array have shown that the jets of the Teacup Galaxy, although relatively weak, move heat and accelerate the gas of the galaxy, even in the case of radio-silent galaxies. Jets can redistribute and alter the surrounding gas, which affects the galaxy's ability. Christina Rausalita, an astronomer at the Institute of Astrophysics of the Canary Islands, explains that the effects of these jets do not always occur head-on. The study found that the most significant effects on the Teacup Galaxy occur perpendicular to the jet's direction. This lateral turbulence is caused by shock waves generated by the jet bubble, which heats and inflates gas. These interactions can prevent star formation by preventing the gas from cooling and collapsing to form new stars, while stronger jets can heat the gas in galaxies to such an extent that they slow down their growth, preventing the formation of new stars. Weaker jets, such as those in radio-silent galaxies, also play a key role. These jets can stir the gas in a galaxy, causing it to move and be redistributed. This activity can lead to the formation of new structures within the galaxy and affect its long-term evolution. Understanding the influence of these jets allows astronomers to reconstruct the complex puzzle of galaxy formation. Supermassive black holes are an intrinsic part of the life cycle of galaxies, from the dramatic changes caused by powerful jets to the more subtle but significant effects of weaker ones. Stay tuned as we explore together the forces that shape our universe. Our universe hides a mystery that has captivated the human mind for a long time. A question that bridges the known and unknown, the simple and complex. Here on Earth, life thrives in a continuous movement of order and chaos. Every life form is evidence of a hidden order, a pattern woven into the very fabric of existence, from the smallest microorganisms to the largest mammal. But what if the complexity of life, the very essence of our existence, could be explained through a mathematical framework, not only through the lens of biology? This is the territory of assembly theory, a revolutionary concept that transcends traditional science's boundaries. It is a journey into a world where mathematics and biology converge, revealing life's hidden architecture. Imagine a universe in which the secrets of life, from the simplest molecule to the most complex organism, are encoded in mathematical language and waiting to be decoded, where the line between the living and the inert blurs, giving rise to new possibilities and new knowledge. Let's explore how this revolutionary idea is changing our perception of life, evolution, and the cosmos itself. And perhaps we can even get closer to answering a fundamental question. What is the true nature of life in the universe? Since the dawn of civilization, mathematics has been a language of the universe and a tool for deciphering the mysteries of nature. But how does this language of numbers and equations relate to understanding the very essence of life at its core? Assembly theory offers a profound but simple idea. Life's complexity can be measured and understood through a mathematical lens. Let's think of life as a puzzle where each piece represents a molecular block. Assembly theory seeks to show how these pieces come together, step by step, to form the complex structures that define living organisms. Each step in this assembly process represents a leap in complexity, from simple atoms to complex proteins. The theory introduces the concept of the assembly index, the cornerstone of this theory, which measures the steps needed to build a biological structure. It is a numerical value that captures the essence of complexity by quantifying the immeasurable. But how does the standard model of physics fit into all this? The standard model of physics describes the fundamental particles and forces that govern our universe. It seems completely separate from the complexities of biology. However, assembly theory bridges these fields. In assembly theory, the standard model lays the foundation for understanding forces and interactions. It is a bridge between the microscopic world of quarks and leptons and the macroscopic world of living beings. Another important element of the theory is the concept of studying dynamic systems, phase space. This is a mathematical concept used to describe all possible states of a system in assembly theory. The phase space allows us to trace the path of the assembly of life from a single point that represents the simplest form of life. The phase space expands, branching into almost infinite possibilities. Each path represents a different route that life can take across this unlimited mathematical landscape. The trajectories of evolution and its complexities unfold in this mathematical framework, which offers us a new perspective on the complexity of life. It is not only about the particles and forces described by the standard model, but also about how these elements combine and interact over time to create the diverse patterns of life that we see around us. This is where the chaos of random molecular interactions yields to the order of living structures. So let us ask ourselves this question: are the complexities of life simply a product of chance, or is there a deeper cause? Let us consider two very contrasting concepts: complexity and entropy. Entropy is a measure of disorder, of randomness, which seems to be in contradiction with the complexity that we observe in life. How do these opposing forces coexist in the natural world? This is where assembly theory offers a revolutionary perspective. A central element of assembly theory is the assembly index, a revolutionary tool that is designed to measure life's complexity. Think of it as a cosmic rule measuring the steps to assemble a biological structure from its simplest components. Imagine a single molecule as the starting point on the scale. As you ascend the scale, each step represents a more complex assembly, from molecules to cells and beyond. The higher the index, the greater the complexity, and the less likely it is that the structure has arisen by chance. Now let us delve into the interaction between entropy and delve into the interaction between entropy and complexity. Entropy, rooted in thermodynamics, suggests that systems naturally tend toward disorder. However, life defies this trend, evolving from simple origins to a variety of forms combined into the complex, ordered structures that we see today. How does assembly theory resolve this apparent contradiction? It suggests that life is inherently a process of overcoming entropy. Through the assembly index, we see that life's complexity is not a challenge to entropy, but a journey through it. If we consider the beginnings of the Earth, a primordial soup of simple molecules driven by the laws of physics and chemistry, these molecules began to assemble the Earth, a primordial soup of simple molecules, driven for millennia by the laws of physics and chemistry. these molecules began to assemble into more complex structures. Each step along the way marked a victory over entropy, a step toward greater complexity in life. By rethinking evolution through assembly theory, we do not see it as a mere biological process, but as a mathematical inevitability. The emergence and evolution of life became a story of increasing complexity, written in the language of mathematics. Let us now move on to a very trivial question, but one that offers us a new perspective. Are we alone? The search for extraterrestrial life has captivated our imagination for centuries. Now, thanks to assembly theory, we have a new tool in this cosmic search. Assembly theory offers a unique approach to detecting extraterrestrial life. It is not about scanning the sky for radio signals or analyzing light spectra for oxygen, but understanding the complexity of molecules and structures that may indicate life. Let us imagine scanning the atmosphere of a distant exoplanet or the surface of a moon in our solar system. Using assembly theory, we could analyze the molecular complexity of samples for patterns indicating the presence of life. The higher the assembly index, the more likely it is that these molecules are the result of life and not of random processes. However, the path to discovering extraterrestrial life is full of challenges and limitations. One of the biggest obstacles is our understanding of life itself. Our definition of life is based on what we know about life on Earth. What if it does not meet our biochemical standards? Another problem is the immensity of space. The universe is vast, and our ability to explore it is limited by current technology. Even with the most sophisticated telescopes and probes, we can only analyze a small fraction of the cosmos. In addition, assembly theory, although powerful, is still in its infancy. It's a new approach, and its application to the search for extraterrestrial life is uncharted territory. There are doubts about its applicability and precision in different environments, especially those very different from terrestrial ones. Despite these problems, the potential of assembly theory in the search for extraterrestrial life is enormous. It could redefine our understanding of life in the universe and open new doors in astrobiology. Thus, assembly theory offers a new way of seeing life, not only as a biological phenomenon, but as an emergent property of cosmic complexity. Let us imagine the early days of our planet, a world in motion, a melting pot for the chemistry of life. Here in this chaotic environment, simple molecules began their journey of assembly, a process governed by the laws of physics and chemistry, but leading to something much deeper: life. According to assembly theory, life arises when these molecular structures reach a level of complexity allowing them to store and reproduce information. Here is where chemical memory comes in, a crucial step in the evolution of life. Chemical memory is the ability of certain molecular structures to retain their structure. In other words, we can say that it is the blueprint of life in the world of assembly theory. This is where reproducibility becomes key. The ability to reproduce these patterns, to transmit them from generation to generation, drives the evolution of life, from the simplest RNA molecules and the primordial soup to the great diversity of life we see today. Each step in this evolutionary journey has been a step forward in assembly index. Each increase in complexity represents a triumph over the entropy that governs the universe. But the story of the origin and evolution of life is not only a story of increasing complexity, it is also a story of resilience and adaptability. Life has found a way to thrive in the most extreme environments, from the depths of the ocean to the confines of space. In scientific discovery, each new theory is analyzed and debated. Assembly theory, a concept that promises to revolutionize our understanding of life and complexity, is now at a crossroads, questioned by critical voices such as Dr. Hector Zinel. The criticism presented by Zinel raises fundamental questions about the future evolution of assembly theory. Encompassing an impressive 18,000 words, the article requires time and reflection, and its dedicated reading can take between 1 and 2 hours. This is not a superficial review of the subject, but a deep immersion into the heart of scientific debate. For those who are interested, We leave a link in the description to both articles, the study and the counterarguments. Looking ahead, the role of assembly theory in scientific research remains uncertain. Will it adapt and overcome these challenges, or will it remain a footnote in the history of science? Despite the disagreements, one thing is clear. The debates surrounding assembly theory have initiated a conversation about the nature of scientific discovery and emphasized the need for rigor, transparency, and humility in the pursuit of knowledge. In the end, the impact of assembly theory on future research may not lie in its specific claims, but in the lessons it teaches us about the scientific process. As we explore the mysteries of life in the universe, these theories will come and go, but the search for understanding, the search to unravel the mysteries of our existence, is always at the center of scientific research. Supernovae are not only amazing events in the universe, but vital cosmic phenomena that shape and create galaxies. These powerful explosions occur at the end of the life cycle of a massive star, expelling elements into space from which new stars, planets, and even life itself are formed. In essence, supernovae serve as both destroyers and creators of galaxies. In the study of supernovae, images play a crucial role in understanding these powerful explosions. Over the years, advances in imaging technology have allowed astronomers to capture spectacular views of supernovae at different stages, revealing intricate details of their structure and the elements they expel into space. The story of Betelgeuse, a red supergiant star, is a perfect example of how images help us understand the behavior of supernovae. Betelgeuse has recently attracted attention due to its sudden fading and increases in brightness. This variability has led to speculation about its imminent explosion, which has aroused great interest. The appearance of a dust cloud around the star, observed in telescopes and captured in images, was initially interpreted as a precursor to a supernova. However, it was later considered a natural phenomenon in the life cycle of red supergiants. So, why did scientists initially hypothesize that this star would be the next supernova observed? This red supergiant occupies a prominent place in the constellation of Orion, on its shoulder, and is visible to observers even with the naked eye. Let's take a look at the life of Betelgeuse, an intriguing journey that will show us the star's evolution from its birth to its current state as a massive pulsating giant approaching the end of its life. Betelgeuse began its existence as a massive star burning hydrogen in its core, like many others. However, due to its large mass, it evolved rapidly, entering successive phases of nuclear fusion. The significant mass of the star distinguished its evolutionary trajectory from the evolution of smaller stars, such as our Sun. While the Sun is currently a stable main sequence star that slowly converts hydrogen into helium, Betelgeuse, due to its much greater mass, more rapidly depleted its hydrogen reserves and evolved into a red supergiant. The key difference between Betelgeuse and our Sun is its mass. Betelgeuse, which is between 15 and 20 times the mass of the Sun, experiences greater pressure and temperature in its core, which accelerates nuclear fusion. The intense fusion causes Betelgeuse to burn its fuel rapidly, resulting in an unstable structure and significant brightness fluctuations. In contrast, the Sun's lower mass allows it to remain stable for billions of years, with a much longer and more stable hydrogen-burning phase. As the juice aged, it entered successive phases of nuclear fusion, gradually burning elements heavier than hydrogen. The internal pressure caused the star to begin to swell, transforming from a main sequence star into a red supergiant. This stage is characterized by the enormous size and variability of Betelgeuse's brightness, and the variability of its brightness. The star expands and contracts as it goes through complex nuclear processes. Recent observations suggest that Betelgeuse may be about to become a supernova. The dimming of the star in 2019, followed by an unexpected increase in its brightness, has led scientists to speculate that it may be approaching the final stage of its life. These changes in brightness are believed to be related to internal processes that could indicate the beginning of the core collapse. The pulsations of the star, with cycles of 1, 85, 230 for 120 and 2,200 days help to understand its internal dynamics. The longest cycle of 2,200 days is particularly intriguing because it could represent the fundamental pulsation mode of Betelgeuse, indicating its advanced stage of evolution. These observations, along with recent telescopic findings, suggest that Betelgeuse may be entering a carbon-burning phase that precedes a supernova explosion. But what are the complex nuclear processes that dictate when the life of a star in the center of a massive star like Betelgeuse must come to an end? Nuclear fusion converts hydrogen to helium, releasing an enormous amount of energy. As the star ages, heavier elements fuse, forming bulbous layers. Finally, the nuclei fill with iron, which cannot release energy during fusion, leading to gravitational collapse. As the core collapses, an uncontrolled reaction triggers. In this process, the iron core collapses under enormous gravitational forces, reaching temperatures of billions of degrees, leading to a rebound effect in which the core inflates and then explodes, creating a shock wave that tears the star apart. A supernova explosion releases an enormous amount of energy, briefly eclipsing an entire galaxy. The mechanics of this process involve complex interaction between nuclear collapse, gravitational forces, and intense heating. The shock wave generated by the core's collapse propagates outward, expelling the outer layers of the star into space. Ancient astronomers recorded these bright phenomena for thousands of years, sometimes describing them as guest stars or new stars. The first recorded observation of a supernova dates to the year 185 DC, when Chinese astronomers observed guest stars, as they called them, that were visible for 8 months. Although they are rare, astronomers continue to study them to this day, especially when they give rise to unusual phenomena, such as gamma-ray bursts. Gamma-ray bursts, or GRBs, are intense bursts of gamma rays usually associated with the collapse of massive stars or the fusion of neutron stars. These bursts are some of the most energetic phenomena in the universe, capable of releasing more energy in seconds than the Sun will emit in its entire life of 10,000 million years. The discovery of GRB Boat, also known as the brightest of all time, in October 2022, was a milestone in GRB observations, surprising astronomers with its unprecedented brightness and shocking effect on Earth. The GRB Boat, officially designated GRB 221009, was detected on October 9, 2022, and originated in a galaxy about 2,400 million light-years from Earth. The event was unusual not only for its brightness, but also for its duration, as it lasted about 7 minutes, much longer than a typical gamma-ray burst. The burst was so powerful that it affected Earth's ionosphere, temporarily disrupting radio communications and altering the atmosphere's ionization. The relationship between supernovas and gamma-ray bursts is complex and fascinating. In some cases, the core collapse of a massive star can trigger a GRB, especially if the star rotates rapidly and has a strong magnetic field. These long GRBs usually last more than 2 seconds and are often followed by a supernova explosion. The GRB was remarkable not only for its brightness, but also for providing information about the formation of heavy elements. In April of this year, scientists studied this burst in detail, with the initial hope that it could provide clues about the origin of elements heavier than iron, which are normally formed in supernova explosions or neutron star mergers. However, subsequent analyses showed that GRBs do not produce these elements, which left scientists even more perplexed and highlighted the mysterious nature of these cosmic phenomena. To find out exactly what caused the flash, scientists used various observational tools, including the James Webb Space Telescope. The flash's exceptional brightness initially obscured its surroundings, making it difficult to observe the accompanying supernova or other objects in the host galaxy. Several months had to pass before the brightness decreased enough to make detailed observations. As a result, a relatively undetectable supernova remnant was detected, which was surprising given the power of the gamma-ray burst. The GRB Boat also provided information about the characteristics of gamma-ray bursts. The exceptional brightness and long duration of this event indicated that the GRB was highly concentrated, with narrow jets pointing directly toward Earth. This narrow direction likely contributed to the intense brightness observed, as gamma-ray bursts tend to be directional phenomena. The burst's narrow jets were probably the result of a rapidly rotating star with a strong magnetic field that produced a powerful and focused flare. While the GRB boat has provided information about gamma-ray bursts and supernovas, scientists continue to seek answers to the mysteries of Betelgeuse. Recent research suggests that Betelgeuse's cycles of darkness and brightness are part of its natural behavior as a variable star. It turns out that, unlike our Sun, Betelgeuse is an extremely explosive and low-density plasma cloud that changes shape frequently, created by scientific simulations that illustrate the behavior of Betelgeuse in periods of brightness and darkness that occur approximately every 400 days, and the longest cycle is about 2,000 days. Recent studies have tried to explain the Great Darkening phenomenon that occurred in 2020, and observations from various telescopes over the last 15 years have provided a lot of information. Observations at various frequencies, including microwaves and infrared, have allowed scientists to penetrate the layers of Betelgeuse and detect silicon monoxide, indicating the presence of a large dust cloud. This discovery refuted the initial speculation that Betelgeuse was about to explode. Instead, it appears that the star's internal activity caused the material to separate, forming a large cloud of gas. The formation of a cold region below this cloud caused the particles to condense, creating a dark cloud that obscured Betelgeuse from view from Earth. More detailed studies of Betelgeuse's behavior revealed that the star had experienced two shock waves, one in 2018 and another a year later. These waves disrupted the surface, creating hot and cold spots, which was confirmed by observations of ultraviolet images from the Hubble Space Telescope. The shock waves and their aftermath disproved the initial hypothesis that Betelgeuse was close to becoming a supernova and, instead, demonstrated that this behavior of the star is part of its natural life cycle. Betelgeuse's behavior is also characterized by its high speed of rotation. Unlike typical red supergiants, which rotate slowly, Betelgeuse rotates at about 3 m per second, which initially led researchers to think that it might be a binary star that had collided. However, recent research suggests that this rotational speed could be influenced by rapidly moving convective cells within the star, contradicting initial hypotheses about its rotational behavior. Despite its unusual behavior, this research suggests that Betelgeuse is unlikely to become a supernova during our lifetime. The current state of the star is more like that of a variable red supergiant approaching the end of its life, but in no case approaching a supernova explosion. So, we come to the question that concerns us all. How would such an explosion affect our planet? The potential impact of a nearby supernova on Earth is a subject of speculation and concern. Although a supernova is not expected to pose an immediate threat to our home, the explosion of a star a few light years away could affect Earth's atmosphere and potentially affect life. For example, the flash from the same GRB was so intense that it significantly affected the terrestrial ionosphere, altering atmospheric conditions and interrupting radio communications. The flash released an enormous amount of energy that interacted with Earth's atmosphere, causing a sudden increase in ionization. This increase in ionization affected the ozone layer and triggered chemical reactions that scientists are still trying to understand. The GRB also interrupted radio signals, especially those used for communication and navigation. The energy released in the explosion was so great that it even blinded several satellites, which demonstrates the enormous power of these cosmic phenomena. However, the explosion itself was observed from a galaxy located a whopping 2,400 million light-years away. This event only highlights the need to continue studying gamma-ray bursts to understand their impact on us, on our planet, and on the universe as a whole. In addition, studies of supernovas also contribute to our understanding of dark matter, dark energy, and the general structure of the universe. Type 1a supernovas, which are binary stellar systems, are crucial for measuring cosmic distances and studying the expansion of the universe. These standard candles have helped astronomers to detect the accelerated expansion of the universe, which in turn has provided context to understand dark energy. Supernovas are a key topic for the astronomy of the future. Their explosive nature and their transforming impact continue to fascinate scientists and inspire new discoveries. While some people are paralyzed by the expectation of the Betelgeuse explosion in live broadcasts on the internet, we look forward to the discoveries of missions such as the Vera Rubin Observatory and the Euclid Telescope, which will contribute to advancing our understanding of supernovas as we delve into space. These stellar explosions will undoubtedly shape our understanding of the universe and our place in it. Music. You have probably heard of dark matter, that elusive substance that constitutes approximately a quarter of the universe, and that, like a ghostly puppeteer, and you have probably heard of dark matter, the elusive substance that constitutes approximately a quarter of the universe, that ghostly puppeteer that pulls the strings of the galaxy without ever showing itself. But dark matter is only the tip of the cosmic iceberg. Imagine a universe in which the balance of gravity is tilted in mysterious ways, where stars and binary systems, two stars orbiting around a common center, defy the very laws established by Newton and Einstein. What if their equations were not the final word? Recent investigations suggest anomalies and deviations in the orbital dance of double stars that neither dark matter nor our current knowledge of gravity can fully explain. Are we facing a paradigm shift? Is our vision of the cosmos not as stable as we thought? In the cosmic ballet, the stars are the prima donnas that call our attention. But have you ever wondered how these celestial stars are formed? Everything begins in the dark and cold corners of a nebula, a vast cloud of gas and dust. Gravity plays a key role here, attracting the particles closer and closer until they stop resisting gravity and merge, triggering a nuclear fusion reaction that gives rise to a star. However, the life of a star does not last forever. There comes a time when the nuclear fuel runs out and the star faces its inevitable disappearance. For massive stars, this end is spectacular. A supernova explosion that eclipses entire galaxies, even if only for a brief moment. These supernovas are not only cosmic fireworks, they're the forges of the universe. It is in the crucible of these explosions where heavier elements than iron are created. So the gold in your jewelry and the calcium in your bones are stardust, the remains of a supernova explosion. But here is where the plot thickens in a universe dominated by dark matter. These stars and their explosive depths are part of a broader scenario. Dark matter, with its gravitational force, influences the formation of galaxies and the distribution of stars within them. Imagine two galaxies, one with dark matter and one without it. In the galaxy with dark matter, the gravitational forces are so strong that they can cause bursts of star formation, which gives rise to a greater number of supernovas. In these galaxies, stars are formed and die at an accelerated rate, creating a dynamic and changing landscape. Studies have quantified this relationship, showing a direct correlation between the amount of dark matter in a galaxy and the rate of star formation. But what if this correlation is not as simple as it seems? Enter modified Newtonian dynamics. This theory suggests that gravity behaves differently at very small accelerations. If it is correct, the high rate of star formation in galaxies rich in dark matter could have an alternative explanation: binary stellar systems. Those cosmic pairs that we have mentioned previously can serve as an ideal test laboratory for these theories. Its orbital dynamics can show if Newtonian gravity persists or if man offers a better explanation as scientists delve into the data, especially in the treasure that the GIA mission has provided us. We are getting closer and closer to understanding the true nature of this galactic dance. In cosmic narratives, dark matter is often represented as a silent and mysterious entity that shapes galaxies, but remains difficult to detect. One of the most compelling theories that attempt to solve this mystery is the cold dark matter model, or CDM. In the CDM model, dark matter is cold, which means that its particles move much more slowly than the speed of light. This slowness allows them to cluster together to form the gravitational scaffolding on which galaxies are built. Computer models based on the CDM have been very successful in reconstructing the large-scale structure of the universe. They show a cosmic network of galaxies connected by filaments of dark matter that is very similar to what we observe. But, as in any good story, there are unexpected twists in the plot. While the CDM does an excellent job explaining the great architecture of the universe, it fails when we get closer to individual galaxies. Take, for example, the rotation curves of galaxies, the speed at which stars and gas rotate around the galactic center. According to Newtonian physics and the CDM model, this speed should decrease drastically as we move away from the center, but the observations tell a different story. The rotation curves remain surprisingly flat, suggesting that there is something else involved here, perhaps another type of dark matter or even a modification of gravity. And then there are dwarf galaxies, smaller satellites of larger galaxies like our own Milky Way. The CDM model predicts many dwarf galaxies, but simply not as many as are expected. These inconsistencies have led scientists to consider alternatives and question the very basis of the CDM model. Could it be incomplete, or are we missing an important piece of the cosmic puzzle? This is where MOND comes onto the scene again, offering a different set of equations that better explain these galactic characteristics. It is as if there were two different scripts for the same film, each with its own interpretation of the main character, dark matter. In the scientific community, there is division. Is CDM the definitive theory that unifies our understanding of the universe, or is it just a step towards a more complete model? For centuries, the equations of Sir Isaac Newton have been the basis for our understanding of gravity. They have been tested, repeated, and verified, and have stood the test of time. But what if there is more? We present MOND, or modified Newtonian dynamics, a theory that dares to modify Newton's sacred equations. It suggests that gravity behaves differently at extremely low accelerations, such as on the outskirts of galaxies. The objective of MOND, conceived by the physicist Murray Milgram in the early 1980s, is to resolve some of the inconsistencies that have arisen in our observations of galaxies, especially in the enigmatic rotation curves that we have discussed previously. As you can see, MOND fits perfectly to the flat rotation curves observed in galaxies without resorting to dark matter. It is as if MOND told us, wait, maybe it is not necessary to invent a mysterious form of matter. Maybe you just have to adjust the equations. It is not just about the rotation curves. MOND has also managed to explain the dynamics of some galaxy clusters and even the large-scale structure of the universe without resorting to mysterious dark matter. But, of course, no theory is without its problems. While MOND is successful in some areas, it faces difficulties in others, such as explaining the cosmic microwave background, the residual glow of the Big Bang. The cosmic microwave background, or CMB, is a snapshot of the universe only 380,000 years after its birth. The CDM model with its dark matter component explains the characteristics of the remnant radiation well. However, MOND has difficulties in this aspect, and let's not forget our celestial pairs, the double star systems, whose recent studies, some of which we have already discussed, have shown contradictory results when applying MOND to them. What does this tell us? At a minimum, a state of exciting uncertainty as a new day arrives, especially since the Gaia mission. MOND remains the subject of heated debate. Is it the missing piece of the puzzle that will finally explain the anomalies we observe, or is it a useful, but ultimately flawed, step towards a more complete theory in a universe full of questions? Sometimes, the answers are found closer to home. Only 15 million kilometers from Earth orbits Gaia, a spacecraft that may hold the keys to some of the most puzzling mysteries of the universe. Launched by the European Space Agency in 2013, Gaia is not just any telescope. It is a spatial cartographer that maps the positions, distances, and movements of more than 1 billion stars with unprecedented precision. Imagine having the coordinates of 1 billion stars at your fingertips. It's like Google Maps for the Milky Way, but with an amazing level of detail. One of Gaia's key techniques is parallax, an ancient method with a modern interpretation. By observing a star from two different points in its orbit, Gaia can triangulate its distance with incredible precision. But Gaia is more than just a space explorer, it is a theory checker. Do you remember those controversial theories about gravity and dark matter? Gaia's data can be used to put those theories under the microscope. Let's take, for example, the double star systems. These systems are crucial for testing theories such as MOND. Gaia's precise measurements of the positions and velocities of these stars can help us understand which theory is correct, and not only stars. Gaia also observes asteroids, planets, and even distant galaxies. Its data has been used to refine the Hubble constant, a key parameter that helps us understand the rate at which the universe expands. The measurement of the Hubble constant with Gaia has added a new twist to the ongoing cosmic controversy. Different methods yielded slightly different values, and Gaia's data became an important piece of this cosmic puzzle. But the Gaia mission is not without its challenges. While the spacecraft provides a wealth of data, interpreting it is another story. The same Gaia data has been used both to support and refute theories such as CDM and MOND, which has led to heated debates within the scientific community. It is like a high-resolution photograph in which everyone sees something different. Is it a reflection in the lens or a revolutionary discovery? The interpretation depends on sophisticated statistical methods and, of course, on our basic hypotheses about the universe. There is nothing more fascinating than double stars, two stars united in a gravitational embrace that orbit one another in a delicate balance of attraction and repulsion. As we mentioned earlier, these dual systems are not only celestial spectacles, but also cosmic laboratories. Here, in the intricate ballet of their orbits, we can test our deepest theories about the nature of gravity. Double stars have been a cornerstone of astronomical research for centuries. They have helped us to measure the massive stars, understand the stellar evolution, and even confirm the general theory of relativity of Einstein. But in the context of our current debate between the cold dark matter and the modified Newtonian dynamics, the double stars play an even more important role. Their orbital dynamics can reveal if Newtonian gravity persists or if MOND offers a better explanation. Recent studies have delved into this question. Some studies using data from the Gaia mission have shown that double stellar systems behave as Newtonian gravity predicts, which calls into question the applicability of MOND. However, other studies tell a different story. They suggest that MOND is better for some binary systems, especially those with large distances and weak gravitational attraction. Could it be that both theories are partially correct, or are we missing a key piece of the puzzle? The scientific community is divided, and with reason, a lot is at stake. The behavior of binary stars could confirm our current theories or make us start from scratch in our search to understand the universe. So, how do we weigh the evidence? Let's get to know the Bayesian statistics, a mathematical framework that could tip the balance, named thus in honor of Thomas Bayes, a statistician and theologian of the 18th century. Bayesian statistics offer a way to update our beliefs in light of new data. It is like a mathematical expression of the scientific method itself. It works like this. One starts from a previous belief or prior, which is the initial hypothesis. As new data becomes available, it is updated before formulating a subsequent hypothesis, a revised hypothesis that better fits the real data in the context of our cosmic debate, whether it is the cold dark matter, or something completely different. Bayesian statistics provide a rigorous way to evaluate which theory is more likely from the observed data. For example, when analyzing double star systems, Bayesian methods can help quantify the probability that MOND or Newtonian gravity is the correct theory. It is not only about adjusting curves, but about estimating the weight of evidence. And it is not only applied to double stars. The Bayesian statistic has been applied to a wide range of cosmic phenomena, from the distribution of the dark matter in the galactic clusters to the rate of expansion of the universe. However, Bayesian methods are not exempt from criticism. One of the most controversial points is the choice of a prior. That is, how to choose the initial hypothesis in a way that does not distort the result. The choice of a prior can be controversial because it can affect the results if the prior leans strongly towards a theory, since a posterior can confirm that theory, even if the other is equally true. While we struggle with these questions, Bayesian statistics remain a powerful tool in our analytical arsenal. It offers a way to make sense of complex data, filter the noise, and find the signal. The universe seems to refuse to reveal its secrets easily, even as we collect more data. The debate about the true nature of gravity is intensifying. Hyun, an astronomer who recently appeared in the headlines, said, "I felt like I was dreaming. It seemed so unreal." This is because my results did not match any of the previous ones. Chase's work stirred the waters by suggesting that when the gravitational acceleration of stars in certain double systems falls below a certain threshold, they are more consistent with MOND models than with the standard gravity model. But here is the problem. Jay's findings contradict several previous studies. He mentions that a group has been claiming for some time that there is an anomaly, but this does not seem to match the predictions of the existing modified theories of gravity. This discrepancy in the results is not just an error, but a fundamental challenge to our understanding of the cosmos. It raises questions about the reliability of our models and the data we use to test them. So what does this bring us? Well, at least a state of productive confusion, as CH concludes. Since standard cosmology is based on general relativity, cosmology needs a major revision. The debate is far from over. As we collect more data and refine our theories, the search for the ultimate truth about gravity and the universe continues. And in this search, each anomaly, each contradictory result adds a new level of complexity and wonder to the field of space exploration. The James Webb Space Telescope is a beacon of human ingenuity and curiosity. Its recent foray into the depths of our solar system has revealed discoveries that challenge the possibility of life beyond Earth. Among the many celestial bodies that orbit our giant neighbor Jupiter, Europa is a world of special interest, with its irregular surface and hidden ocean. This icy moon has long intrigued scientists and dreamers alike. However, the recent discovery by the JWST has put Europa in the spotlight of astrobiological research. The JWST, in an unprecedented observation of the moon, has discovered carbon dioxide on Europa's surface. This discovery, although seemingly simple, has profound implications. Carbon dioxide, an essential molecule for life as we know it here on Earth, could be an indicator of the potential for life on extraterrestrial worlds. Let's delve together into the data obtained by the JWST. What secrets does Europa hide under its ice sheet? Could the discovery of carbon dioxide be a clue about life beyond Earth? Europa, a moon full of mystery, is a strange and fascinating landscape. Its surface is covered by an ice mantle with a complex network of lines and ridges. These characteristics, known as lines, are not only superficial marks, but tell the story of the dynamic geological processes that take place. This ice layer between 9 and 15 kilometers thick hides a vast ocean that has interested scientists for decades. It is believed that the lines on the surface of Europa are the result of the interaction of the ice crust with the underground ocean of the moon. These cracks and ridges form as the ice moves and breaks, a process driven by Europa's movement around Jupiter. Under this icy barrier lies a salty ocean with an estimated depth of between 40 and 90 kilometers. This hidden, dark, and cold sea is kept in a liquid state not by solar heat, but by the so-called tidal deformation. The satellite revolves around its gigantic progenitor and generates enough heat to keep the ocean in a liquid state. The chemical composition of this ocean is a subject of intense research and speculation. It is believed that there may be hydrothermal vents on the ocean floor, similar to those found in the oceans of the Earth. These sources could provide the energy and minerals needed to sustain life, which would make Europa's oceans an ideal candidate in the search for extraterrestrial life. The physical properties of Europa's oceans also raise intriguing questions. The presence of salts and the ability to form complex organic compounds, combined with the energy of hydrothermal activity, creates an environment where life can exist. The oceanic depths and pressures, although extreme, are not beyond habitability, as evidenced by life in Earth's deep trenches. The mysterious environment of Europa, with its icy surface and ocean, is an interesting case for investigation, but what exactly has drawn scientists' attention to this moon? This time, with the help of the JWST, astronomers have made a fascinating discovery using data from the NASA Space Telescope. They have detected carbon dioxide on the satellite's icy surface. This discovery is not only an addition to the chemical profile of Europa, but an important key to understanding its potential for harboring life. Using the near-infrared spectrograph, the JWST discovered carbon dioxide in the geologically young and chaotic area of Terra Regio. This discovery is not limited to the presence of a molecule. It is believed that the carbon dioxide on Europa's surface comes from the interior, from its mysterious underground ocean, and not from external forces such as meteorites. This discovery suggests a dynamic exchange between Europa's ocean and its icy layer. Most interestingly, carbon dioxide is unstable on the surface of Europa, suggesting a constant replenishment from the interior of the moon. The presence of carbon dioxide in the young terrain region indicates a recent and possibly ongoing process. This exchange may be key to understanding the ocean's chemistry and, by extension, its ability to harbor life. This discovery has been possible thanks to the JWST instrument, which has provided detailed spectra of the surface of Europa. The ability to precisely locate specific chemical substances, such as carbon dioxide, allows astronomers to build a more complete picture of Europa's chemical landscape. Each discovery adds a piece to the puzzle of this mysterious moon. But why is this gas released? And, moreover, how is this cosmic body kept warm, allowing the existence of a liquid ocean beneath the surface? Europa, in its gravitational interaction with Jupiter, experiences a phenomenon known as tidal deformation or tidal flexing. This process, caused by tidal flexing, is one of the key factors that determine Europa's potential to harbor life. As Europa revolves around Jupiter, its shape is constantly flexed. This constant flexing generates significant internal heat, a process very different from the solar heating we know on Earth. This internal heating is fundamental, as it is believed to keep Europa's underground ocean in a liquid state despite the relatively low temperature of outer space. The heat generated by tidal deformations can also stimulate geological activity on Europa, such as subglacial volcanism and hydrothermal vents. These openings, if they exist, could be similar to those in Earth's deep oceans, which are teeming with life despite the lack of sunlight. The energy provided by tidal deformations could be a crucial ingredient for life in the ocean. Hydrothermal vents support entire ecosystems in which life forms use the chemical energy released from the vents. On Europa, a similar process could occur, with life forms using the energy from hydrothermal vents to fuel their metabolic processes. In such an environment, life could exist independently of sunlight, depending instead on the chemical and thermal energy provided by Europa's internal dynamics. Carbon dioxide, a molecule so essential for life on Earth, now occupies a central place in the debate about extraterrestrial life beyond our planet. Carbon dioxide is the cornerstone of the biological process of photosynthesis that drives Earth's ecosystems. But what role can this essential molecule play in the cold, alien environment of Europa? The discovery of carbon dioxide on Europa by the James Webb Space Telescope opens up intriguing possibilities in extraterrestrial environments, especially on icy moons like Europa. Carbon dioxide could play a different, but equally important, role in sustaining life in the absence of sunlight. Life in Europa's oceans would have to rely on chemical energy, a concept known as chemosynthesis. This is where carbon dioxide can play a key role. In Earth's deep oceans, some organisms use carbon dioxide combined with hydrogen from hydrothermal vents to create organic matter. This process, although independent of sunlight, is a fundamental aspect of life in extreme environments. The presence of carbon dioxide on Europa could indicate a similar process if hydrothermal vents exist in Europa's oceans, as many scientists believe. These could be the places where life forms use carbon dioxide, perhaps like deep-sea organisms on Earth. This leads us to an intriguing question. Could the carbon dioxide on Europa's surface be a byproduct of biological activity in its oceans? Although the topic remains speculative, this possibility adds an exciting dimension to the search for life beyond Earth. The role of carbon dioxide in extraterrestrial biological processes is a subject of intense research and speculation. Its presence on an icy moon could be an indicator of the potential for life in environments far removed from the sunny world we know. Let's summarize. The key to Europa's potential habitability lies in three basic elements: liquid water, a source of energy, and the necessary chemical elements, such as carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Europa's underground ocean and the energy generated by the tides meet the first two requirements, and the presence of carbon dioxide on its surface points to the presence of the necessary elements. The detection of carbon dioxide on Europa is an important piece of the puzzle. On Earth, carbon dioxide is essential for life, as it plays a fundamental role in both photosynthesis and respiration. In the alien environment of Europa, this molecule could be equally important, potentially acting as a building block or as part of the metabolic processes of hypothetical life forms. The presence of carbon dioxide also suggests that Europa's environment is chemically active, a key factor in the search for life. This activity could indicate geological processes or even hint at biological ones if life existed there. It is also possible to emphasize the importance of studying Europa's ocean as a testing ground for the origin of life. The conditions on Europa could be similar to those of primitive Earth, which would give us a rough idea of how life could have arisen in extreme conditions. On Earth, carbon dioxide is a fundamental component of life, involved in processes such as photosynthesis and respiration. In the alien environment of Europa, this molecule could play a similar role, potentially serving as a building block or as part of the metabolic processes of a life form. Carbon dioxide could be a byproduct or a resource of biological activity. On the threshold of a new era in astrobiology, the importance of the James Webb Space Telescope's discoveries propels us towards a future full of possibilities. The upcoming missions to Europa, in particular that of the European Space Agency and NASA's Europa Clipper, are designed to expand our horizons and deepen our understanding of this enigmatic moon. The JUICE mission, launched on April 14, 2023, aims to carry out detailed observations of Jupiter and its three large icy satellites, with special attention to Ganymede. However, the study of Europa will provide important data that will complement the findings of the JWST by offering information about the ice crust of Europa and its underground ocean. In turn, the NASA Europa Clipper, whose launch is scheduled for October 2024, is specifically designed to study Europa and is equipped with a set of sophisticated instruments. This mission will carry out a detailed reconnaissance of Europa's ice layer and underground ocean in search of signs of habitability. The goal of these missions is to take advantage of the revolutionary discoveries of the JWST to delve into the mysteries of the environment of Europa, meticulously examining its surface, analyzing its ocean, and looking for biochemical signals. These missions will improve our understanding of this moon's potential to harbor life. By the way, you still have a unique opportunity to be part of this historic exploration and go down in the history of this extraordinary moon. Quoting NASA, join the mission and record your name on the NASA Europa Clipper spacecraft as it travels 18 billion miles to explore Europa, an oceanic world that may harbor life. Sign up today at the message in a bottle. End quote. Imagine, in an era in which some people have not even visited the neighboring country, a piece of your personal history will travel such a distance to orbit another planet. A truly fascinating idea. By adding your name, you're not only leaving a personal mark, you'll be part of a legacy that will resonate in the annals of space exploration. Europa, once a distant and icy moon, is now the center of our search to understand the existence of life beyond Earth. The results from the JWST, combined with the future studies of JUICE and the Europa Clipper, mark the beginning of a new era of astrobiology, an era in which the search for extraterrestrial life is moving from the realm of speculation to reality in the vastness of our solar system. Beyond the asteroid belt and gas giants lies a world shrouded in mystery. Neptune, the eighth planet from our Sun, a distant ice giant, has captured our imagination for decades. We have imagined it as a dark blue sphere on the edge of our cosmic neighborhood. But what if the vision of this distant world was an elaborate illusion? This mysterious planet, named after the Roman god of the sea, has hidden its true colors from us, wrapped in a veil of deep blue. Neptune has been the subject of many stories and scientific investigations, but recent discoveries have eliminated this blue facade, revealing a much more complex and fascinating reality than we could have imagined for years. Our telescopes have been pointed towards this distant giant, capturing its essence in pixels and data. However, what we saw was not the reality of the planet, but a reflection of our own technological and perceptive limitations. The deep blue color that we associated with Neptune was actually the result of our own interpretations and enhancements, a story that we created and believed without knowing it. Today we invite you to explore Neptune like never before, to delve into its true colors, to understand its dynamic atmosphere, and unravel the secrets of its moons and rings. For centuries, Neptune was represented as a dark blue world whose color reflected its cold and distant nature in the solar system. This representation, deeply rooted in our collective consciousness, has become the cornerstone of our understanding of this ice giant. But what if this image is a reflection of our perceptions rather than the true appearance of the planet? Its true appearance. The color of Neptune is a story of scientific evolution and the search for truth. It begins with the Voyager 2 probe, launched by NASA in 1977 and sent to the confines of the solar system. It took the first close-up images of Neptune, painting a picture of the planet bathed in a stunning blue color. However, these images were not a direct window to Neptune's true color, but interpretations, the result of processing the data through the prism of human understanding and the technological capabilities of the time. The intense blue color we saw was the product of enhancements made by scientists to highlight certain characteristics of the planet. This story began to unfold with the arrival of more advanced telescopes, such as the Hubble Space Telescope and the Very Large Telescope. These instruments, equipped with state-of-the-art technology, allowed astronomers to see the planet's true color again. The results of this study were surprising. The new images revealed that the color of Neptune was not the previous deep blue, but a more muted and varied tone. This discovery was not only aesthetic, but a fundamental change in our understanding of the planet. The reason for this error in color lies in the way we process and interpret astronomical data. The colors in space images are often enhanced or altered to emphasize certain features or to make them more distinguishable to the human eye. In the case of Neptune, these enhancements over time have led to a collective opinion about its deep blue color. What led to this discovery? The key lies in a meticulous study titled Modeling of the Seasonal Cycle of the Color and Magnitude of Uranus in Comparison with Neptune. This study, led by Patrick G.J. Irwin of the University of Oxford, along with a team of experts, set out to unravel seasonal color change mysteries. However, their journey shed light on Neptune's true colors, refuting ingrained beliefs. The team carefully analyzed a large amount of data obtained from the L Observatory for 6 decades. This data, complemented by observations from the Hubble Space Telescope, produced a detailed image of the average color and photometric magnitude of Uranus, revealing its complex seasonal changes. One of the most important aspects of this study was the focus on the reflectivity of Uranus and the abundance of methane. The researchers unraveled a complex relationship between the lower methane content in the polar latitudes and the different reflectivity of aerosol particles. It is believed that this complex interaction of elements in Uranus' atmosphere is influenced by the presence of methane ice particles, which adds a new layer to our understanding. In parallel, the study allowed a fascinating comparison to Neptune. Contrary to popular belief, The difference in blue tones between Neptune and Uranus was less pronounced than expected. This discovery was the result of a critical reassessment of the color of Neptune, which belied the image of the deep blue that had taken root in our minds. The team's methodology was a combination of quantitative analysis, atmospheric modeling, and advanced spectroscopic observations. They converted the measured reflection spectra into radiance and then into tri-stimulus values. This process mimicked the visible colors of the planets as perceived by the human eye. To bridge the gap between raw data and our visual interpretation, the use of advanced telescopes such as the Hubble and the Very Large Telescope played an important role. These technological wonders allowed the team to review and re-examine the true colors of Uranus and, by extension, Neptune, with unprecedented precision. As we delve into the mysteries of Neptune, we find ourselves amid a whirlwind of atmospheric activity that contrasts with the relative calm of its stellar neighbor, Uranus. Neptune's atmosphere, a turbulent and dynamic formation, is home to some of the most extreme weather phenomena in our solar system. One of the most striking features of Neptune's atmosphere is the presence of colossal storms, the most famous of which was the Great Dark Spot discovered by the Voyager spacecraft in 1989. This enormous storm, similar to those of Jupiter, is a testament to the planet's turbulent nature. A great dark spot, a giant rotating storm, offers a window into Neptune's intense atmospheric dynamics. These storms are caused by the strongest winds in the solar system, reaching speeds of up to 1,300 miles per hour. However, to this day, the power and magnitude of these winds remain a mystery to scientists, raising questions about their origin and the energy sources that drive them. In contrast, its neighbor Uranus presents an image of tranquility. Its atmosphere, although composed of hydrogen, helium, and methane, does not present the same violent storms or extreme winds as Neptune. The difference in atmospheric activity between these two ice giants is one of the many mysteries of our solar system. Another intriguing aspect of Neptune's atmosphere is the presence of unusual hot spots, where temperatures can reach 750 degrees Kelvin. These hot spots represent a paradox, as they exist on a planet so far from the sun. The origin of this heat remains a mystery, but theories suggest it could be caused by internal processes such as auroras or magnetic reconnection in the plasma layers. The origin of these hot spots and Neptune's extreme climatic conditions are the subject of ongoing research. They force us to seek new answers to questions about planetary atmospheres and point to complex internal processes that are not yet understood. As we leave the turbulent sphere of Neptune, we enter a realm of celestial harmony where the moons and rings revolve around this ice giant. By turning our gaze towards Triton, Neptune's largest and most intriguing moon, we discover a world of seasonal changes and atmospheric mysteries. Triton, a unique moon with a retrograde orbit, was the last solid object visited by the Voyager spacecraft during its historic journey through the outer solar system. Due to its retrograde orbit, which indicates that it was captured by Neptune's gravity, Triton stands out among the moons in our solar system. Its surface, covered in nitrogen ice, is geologically young and active, with dark streaks indicating the presence of geysers that expel nitrogen gas. Triton's thin atmosphere, whose thickness varies with the seasons, offers a fascinating study of extraterrestrial meteorology. Observations made with its large telescope have revealed that Triton's southern hemisphere is in the middle of summer. This distant moon, despite its relative distance from the sun, is experiencing significant atmospheric changes. The summer sun's heat causes the thin layer of frozen nitrogen, methane, and carbon monoxide on Triton's surface to sublimate and turn into gas. This process causes the icy atmosphere to thicken as the season progresses in Neptune's orbit, 165 times larger than Earth's, around the Sun. The season on Triton lasts more than 40 years, and the southern summer solstice occurred in 2000. The discovery of carbon monoxide in Triton's atmosphere, as well as the confirmation of the presence of methane, was a significant advance in our understanding of this moon. The presence of these gases, especially the enrichment of the upper surface with carbon monoxide, fuels the atmosphere and determines its seasonal dynamics. These findings required a revision of Triton's climatic and atmospheric models. The complex interaction between nitrogen, methane, and carbon monoxide not only determines atmospheric conditions, but also provides information about the Moon's geological and climatic history. But Triton is not alone. The planet is accompanied by a retinue of smaller moons, each of which contributes to our understanding of this distant world. These moons also exhibit seasonal changes and provide information about the complex gravitational interactions and environmental conditions around Neptune. When we turn our gaze from the moons to Neptune's rings, we find another aspect of this planet's mysterious nature. Neptune's rings, formed by a mixture of dust and ice particles, are faint but fascinating and bear witness to the planet's dynamic history. Scientists believe that they are remains of moons that were destroyed by collisions and torn apart by the gravity of Neptune. The composition and characteristics of these rings are closely related to the real color of Neptune and the atmospheric phenomena. The subtle tone of the rings, which is affected by the dispersion of light in the atmosphere of Neptune, adds another layer to the color palette of the planet. The rings, which reflect and refract the light of the sun, create the general appearance of Neptune seen from afar. In 2022, the James Webb Telescope captured the sharpest image of this distant planet's rings in 30 years, photographed with clarity. These rings have changed our thinking about this distant planet. The most striking thing about the new Webb image is the clear view of Neptune's rings. Some of these faint and dusty rings have not been detected since the historic flyby of the Voyager in 1989. The Webb telescope, with its enhanced capabilities, has refocused on these elusive rings. The rings of Neptune are formed by several bands of bright, narrow dust, as well as other fainter ones. The infrared images of the Webb telescope have put these rings under a new light, revealing characteristics that were previously hidden in the darkness of space. It is the first time that these rings have been seen in the infrared spectrum, providing new knowledge about their composition and behavior. The rings of Neptune, like the planet itself, are characterized by a unique composition, different from that of the gas giants Jupiter and Saturn. Neptune is an ice giant rich in elements heavier than hydrogen and helium. This composition is also reflected in the characteristic blue color, invisible in wavelengths caused by a small amount of methane gas in infrared images taken by webcams near the near-infrared camera. Neptune does not appear blue, in contrast to the obscured appearance that would be expected due to the absorption of light and infrared by methane. In images taken by the Space Telescope, Neptune appears as a luminous, bright white sphere. This absorption also affects the appearance of the rings of Neptune, since they reflect and refract the light that travels through them. This unexpected brightness in the infrared results from a unique interaction between the planet's atmosphere and light. While methane gas absorbs red and infrared light, the high-altitude clouds of Neptune's atmosphere reflect sunlight before it is absorbed. In the infrared spectrum, methane ice clouds appear as bright streaks and spots that cast a ghostly glow on the planet. By the way, you may wonder why Triton looks like a dazzling point of light adorned with bright spikes, in contrast to the fainter image of Neptune. These diffraction spike patterns are a feature of the imaging telescope. They are not physical structures, but optical artifacts created by the design of the telescope. The light from Triton that passes through the mirrors and structure of the telescope is diffracted, giving rise to these striking peaks emitted by the moon. In simple terms, diffraction is what happens when a wave, such as light, travels through a small opening or around the edge of an object. Imagine light as water waves flowing through a narrow slit in a wall. When the waves pass through the slit, they deviate in different directions instead of going straight. This propagation of waves after passing through a hole or around an edge is diffraction. In the context of the James Webb Space Telescope and its images, diffraction spikes arise due to the arrangement of the mirrors and structure of the telescope. When light from a bright object, such as a star or Triton in the images of Neptune, enters the telescope, it is slightly deflected by the edges of the mirrors and other parts of the telescope. As a result of this deviation, the light is scattered and forms the star-shaped peaks seen in the images. The study of the rings of Neptune, especially in the infrared, provides valuable information about the atmospheric conditions and the internal composition of the planet. The interaction of the rings with Neptune's atmosphere, particularly with the methane ice clouds, provides information about the bright equatorial band that surrounds the planet gives clues about the global atmospheric circulation, a key factor in the planet's storms. The atmosphere, which descends and heats up near the equator, shines more intensely in the infrared than the colder gases that surround it. As we conclude our journey through the mysterious world of Neptune, we reflect on the impact that these discoveries are having on the broad field of planetary science and the exploration of exoplanets. Neptune, once a distant blue dot, is now a testament to space exploration. The dynamic and constantly evolving discoveries about the true color of Neptune, its atmospheric phenomena, and the intricate details of its rings and moons go far beyond our solar system and provide a crucial example for understanding similar IED, giants, and exoplanets in the confines of our galaxy. The knowledge acquired about Neptune will help astronomers decipher the mysteries of these distant worlds and will enrich our knowledge of the universe as we continue to contemplate the cosmos. Neptune reminds us of the unlimited potential of discovery. His example encourages us to continue searching and unraveling the mysteries of the universe in the 21st century. Humanity is at a crossroads, at a moment in history when we can see the stars but not touch them yet. Born in the era between the exploration of our planet and the possibility of reaching other worlds, we find ourselves at the threshold of an extraordinary journey. It is not only about rockets or physics, but about our survival and our place in the universe. Let us imagine a future in which the Earth faces an existential threat, a catastrophic collision with an asteroid, a climatic collapse, or something completely unpredictable. Our solution is to build generational ships, colossal spaceships that serve as floating cities where multiple generations are born, live, and die while traveling to another star, to a new home. Einstein's special theory of relativity tells us that traveling faster than light is impossible. However, space is within our reach, even at a speed that is only a fraction of the speed of light. Generational ships, traveling at a significant fraction of the speed of light, could travel great distances between the stars with technology such as matter and antimatter engines, compact fusion thrusters, and even black hole propulsion. What seems like science fiction could become reality, but these ships are not just boats, they're lifeboats for humanity. They must sustain life for centuries, perhaps millennia, facing the challenges of space travel, genetic diversity, and mental health. Each ship will be a microcosm of Earth with its social structures, cultural heritage, and daily challenges. What will be needed to construct a ship like that? How could its inhabitants thrive and survive? Join us as we delve into the complexities of interstellar travel without exceeding light speed. Today we will try to unravel the secrets of how humanity may one day travel to the stars, not instantly, but over generations. Planning interstellar travel is not only a matter of technology, but also predicting why it might become necessary. The foreseeable threats to human survival may force us to seek refuge beyond our solar system. Understanding these threats will help us prepare for possible future scenarios that could force humanity to embark on such an extraordinary journey. One of the most immediate threats comes from space itself. The impacts of comets throughout the history of the Earth repeat the history of the Earth. Collisions with comets and asteroids have caused mass extinctions and major climate shifts. A sufficiently strong collision could make Earth uninhabitable, forcing us to seek a new home among the stars. Another serious threat is climate collapse. Human activity has already caused significant changes in our climate: rising temperatures, melting ice caps, and increasingly severe weather. If these trends are not controlled, the Earth could become hostile to human life, which would make the search for habitable exoplanets an absolute priority. Technological progress, while bringing enormous benefits, also carries considerable risks. Advances in artificial intelligence, biotechnology, and autonomous systems could lead to scenarios in which humanity faces a threat from its own creations. Uncontrolled artificial intelligence or modified pathogens could become existential risks, leading to the need to establish human colonies on distant worlds as a defense for our species in search of a new home. Proxima Centauri b is an ideal candidate, located only 24 light-years away in the Alpha Centauri system. It is the closest known exoplanet that is in the habitable zone of its star. As many know, this zone, often referred to as the Goldilocks zone, is the area around a star where conditions may be optimal for the existence of liquid water, an essential ingredient for the life of humanity. Proxima Centauri b was discovered in 2016 and has been the subject of intense study ever since. It orbits a red dwarf star that is smaller and colder than our Sun, meaning the planet would have to be much closer to its star to be within a habitable zone. This proximity, although favorable for retaining heat, also exposes the planet to eruptions and radiation, which must be considered when planning human habitability. Current research indicates that the planet has a mass similar to that of Earth and may have a rocky surface, but much is still unknown about it, including the composition of its atmosphere and the presence of liquid water. Future missions and observations will be necessary to gather more data and assess its suitability for life. Sending a spacecraft to our nearest star involves not only traveling the distance, but also ensuring the destination is suitable for human life. This requires a multifaceted approach that includes robotic probes and telescopes to gather detailed information about the planet's environment. These missions will help determine the feasibility of establishing a human colony and the preparations necessary for long-term survival. Proxima Centauri b was chosen as our target due to its relative proximity and potential habitability. However, reaching and inhabiting that distant world will be a monumental task, requiring an unprecedented level of planning, innovation, and collaboration. The dream of exploring the stars has always been tempered by the harsh realities of physics and time. Traditional concepts of space travel, in which a crew departs and arrives at its destination within their lifetime, seem increasingly impractical when it comes to the vast distances between stars. This is where the concept of intergenerational ships comes into play, a bold and innovative solution to the problem of long-distance space travel. Generation ships, also known as interstellar arcs or generation ships, are designed to sustain people for centuries or even millennia. These ships are self-sufficient ecosystems with not only a crew on board, but all of their descendants. Life on a generation ship is designed to mimic a small, autonomous world with living areas, food production, water recycling, and social systems. The concept is simple, yet profound. As the original crew ages and eventually passes away, their children and their children's children continue the mission. This life cycle ensures that, over many generations, the ship will continue its journey, and each new generation will be trained and prepared to maintain the ship and eventually reach its destination. This approach to space travel requires careful planning and robust systems to ensure the inhabitants thrive and survive. Every aspect of life must be carefully considered, from genetic diversity to ensure a healthy population to cultural and educational programs that preserve and transmit vital knowledge and skills. Einstein's special theory of relativity poses a significant problem for traveling faster than light. According to this theory, as objects approach the speed of light, their mass increases, and they require exponentially more energy to continue accelerating. This makes traveling faster than light impossible with our current understanding of physics. Generation ships offer a practical solution within the framework of Einstein's theory by accepting the duration of space travel and planning for generations of life aboard such ships. Humanity can aspire to reach distant stars. This approach recognizes the limitations imposed by the theory of relativity, while supporting the resilience and adaptability of the human spirit. traveling to the stars requires overcoming significant challenges, among which the enormous distances between celestial bodies stand out. To make interstellar travel feasible within a human lifetime, we must take a closer look at advanced propulsion techniques and the intriguing phenomenon of relativistic time dilation. The relativistic dilation of time is a consequence of the special theory of relativity of Einstein. When an object approaches the speed of light, the time on board slows down in comparison with the time experienced by an observer at rest. This means that, for a spacecraft that travels to a significant fraction of the speed of light, the travel time of the crew will be shortened in comparison with that of those who remain on Earth. For example, if a ship could travel at 90% of the speed of light, the dilation of time would cause 1 year on board the ship to be equivalent to more than 2 years on Earth. Due to this effect, interstellar journeys that last decades or centuries may seem shorter for the crew, although the actual distance does not shrink. Several advanced propulsion methods have been proposed for reaching the high speeds needed for interstellar travel. Each method has its own potential advantages and problems. For example, propulsion by antimatter involves the annihilation of matter and antimatter with the release of enormous amounts of energy. This reaction releases energy far more efficiently than chemical rockets, potentially allowing spacecraft to reach significant fractions of light speed. However, producing and storing enough antimatter remains a major technical hurdle. On the other hand, compact fusion reactors use nuclear fusion, the same process that powers the sun, to produce energy by combining light atomic nuclei, such as hydrogen, in a heavier nuclei. These reactors could provide sustained and powerful thrust for spacecraft. While controlled fusion technology is promising, it is still in the development phase, and the construction of a compact and reliable reactor suitable for space flights is another major engineering challenge. Black hole propulsion is a more speculative concept that consists of taking advantage of the enormous gravitational energy of a black hole to propel a spacecraft. The idea is to create a small, artificial black hole and take advantage of the energy from Hawking radiation it emits. In theory, this method could provide continuous, powerful acceleration, but the technology to create and control artificial black holes remains fantastical, far beyond our current capabilities. However, the problems are not only with thrusters that travel at speeds close to light, as these entail many dangers. One of the main dangers is the threat posed by interstellar particles. At these speeds, even the smallest particles can cause significant damage upon collision. Spacecraft must be equipped with advanced shielding to protect against these high-energy collisions. Radiation is another serious danger. High-speed space travel exposes the crew to intense cosmic radiation, which can have harmful health effects. It will be necessary to have effective protection against radiation and even medical intervention to maintain a healthy crew during long-duration missions. It is also essential to maintain the structural integrity of the spacecraft in the long term. The stresses and deformations of high-speed flight can weaken materials over time, requiring advanced construction techniques and regular maintenance to keep the spacecraft safe and functional throughout the journey. Despite these formidable challenges, the pursuit of interstellar travel drives human ambition and ingenuity. Through research and development of advanced propulsion techniques and overcoming the dangers of high-speed travel, we are taking crucial steps to reach the stars and expand our presence in space. Choosing the right propulsion system for interstellar travel is a critical decision in mission planning. The propulsion system determines the speed, duration, and feasibility of the mission, so it is important to explore both best practices and traditional methods. A promising approach involves expanding traditional propulsion technologies. NASA's Parker Solar Probe uses chemical propulsion and gravitational assist to reach unprecedented speeds. The probe travels at more than 430,000 miles per hour, which is approximately 0.064% of the speed of light, making it the fastest man-made object to date. Its propulsion system is based on solar-powered hydrogen thrusters, demonstrating the potential of existing technology for high-speed space travel. Gravitational assists, or slingshot maneuvers, use the gravity of planets or other celestial bodies to increase a spacecraft's speed without using additional fuel. Through careful trajectory planning, a spacecraft can gain significant speed, reducing travel time over great distances. This technique, while insufficient alone for interstellar travel, can be an important component of a multi-stage propulsion strategy. Expanding these traditional technologies involves developing more efficient thrusters and using larger amounts of fuel. Another promising area is innovation in ion thrusters, which use electric fields to accelerate ions and create thrust. Ion thrusters are very efficient and can operate for extended periods, making them suitable for long-duration missions. Combining these advanced conventional methods could be a practical solution for the initial stages of interstellar travel. To travel faster, we must consider more advanced propulsion methods, such as nuclear propulsion. One of the most intriguing concepts in this category is Project Orion, first proposed in the 1950s. This method consists of a series of thermonuclear explosions behind the spacecraft, each of which creates a powerful thrust to propel the ship forward. Project Orion uses a large pusher plate at the rear of the ship, designed to absorb the shock waves from the explosions and convert them into forward momentum. By repeating this process in a controlled manner, the spacecraft will be able to reach significant fractions of the speed of light, drastically shortening the flight time to nearby stars. Although the concept is theoretically sound, many technical and safety problems remain unsolved. Controlling the timing and direction of the explosions requires precise design, and, in turn, the spacecraft must be designed to withstand enormous loads. In addition, the environmental impact of launching such a vehicle from Earth must be taken into account, which could also require space launch platforms. Another fusion engine concept is the Daedalus project, which involves using fusion reactions to propel a spacecraft. This method involves the use of small pellets of fusion fuel, such as deuterium and helium-3, which are ignited by electron beams to create a constant thrust. The Daedalus project aims to reach speeds of up to 12% of the speed of light, which would allow travel to the nearest stars in the course of a human life. Propulsion by fusion offers a more controllable and potentially safer alternative than the Orion method. However, the technology to build reliable and efficient fusion reactors for spaceflight is still in development. Significant advances in the research and the engineering of the fusion are needed so that this approach is viable for interstellar missions. Choosing the adequate propulsion system is a balance between viability, safety, and performance. The traditional methods, like the ones used in the Parker Solar Probe, offer practical solutions in the short term, while the advanced concepts of propulsion by fusion, like the Orion and Daedalus projects, promise the possibility of faster and more ambitious interstellar travels, guaranteeing the survival and the health of the crew during several generations. One of the most important aspects is to maintain the genetic diversity necessary to prevent the inbreeding and the genetic illnesses that could put the mission in danger. To solve the problem of genetic diversity, scientists use Monte Carlo simulations. These models use statistical methods to simulate and predict the genetic variability throughout many generations, introducing diverse parameters, like the initial size of the population, the mutation rates, and the reproductive patterns. These simulations can provide information on the genetic health of a population over time. The Monte Carlo simulations help to determine the minimum size of the population needed to maintain the genetic diversity and to prevent the depression by inbreeding. They also take into account possible random events, like accidents or illnesses, that could affect the population. This type of model is essential to create a sustainable human colony that can thrive for centuries. Maintaining the genetic diversity requires a careful planning of the reproductive strategies and a possible genetic screening. The crew must receive training on the importance of genetic health and the necessary measures to maintain it. This includes monitoring genetic diversity and making informed decisions about relationships and reproduction. Investigations show that a minimum initial population of at least 100 individuals is required to maintain genetic health over several generations. This figure comes from studies carried out by scientists like Frederick Moran and Camille Ballouy, who have exhaustively studied the genetic dynamics of small, isolated populations. In their investigation, Moran and Ballouy used Monte Carlo simulations to explore different scenarios, including different population sizes and reproductive strategies. Their study shows that, with a balanced sex ratio and an optimal reproductive rate, an initial population of at least 100 can maintain a healthy genetic pool. This population size guarantees that the genetic drift and the inbreeding do not put in danger the health and the viability of the future generations. An initial population of 100 individuals should grow to reach 500 individuals over several generations. This growth is necessary to create a stable and resilient population that can face unforeseen challenges. The model takes into account diverse factors, like random genetic mutations, environmental influences, and possible catastrophes, to guarantee the sustainability of the population. The design of a generational ship to accommodate a growing population implies planning adequate living space, resources, and social structures. The ship must provide educational, sanitary, and recreational facilities to support the physical and mental well-being of the crew. This includes spaces for collaborative activities and private accommodations to provide a balance between social interaction and personal privacy. Beyond the physical infrastructure, it is vital to maintain social cohesion and cultural continuity. The crew must develop a shared sense of purpose and identity to foster cooperation and sustainability. Cultural and educational programs play a key role in maintaining the knowledge and values necessary for the success of the mission. Effective planning of the crew and population is essential for the success of a generational ship. By means of advanced genetic simulations and the investigation, we can guarantee that the population stays healthy and viable with a careful planning and a commitment with the maintenance of the social and genetic health. Humanity can thrive on the way to the stars, guaranteeing the survival and prosperity of future generations. However, above all, designing a generational ship capable of sustaining human life for centuries implies creating a self-sufficient environment that imitates the basic aspects of life on Earth. This includes creating artificial gravity, producing food, and recycling vital resources like water and air. These systems must be reliable, efficient, and capable of functioning autonomously for long periods. One of the most important aspects of the design of the ship is the creation of artificial gravity to maintain the health and the well-being of the crew. Prolonged exposure to microgravity can cause muscular atrophy, loss of bone density, and other health problems. To counteract these effects, the generational ships can use rotating means to create a centrifugal force that imitates the gravity of the Earth. The most practical design consists of a large rotating ring or cylindrical section where the crew lives and works. As the structure rotates at a certain speed, the centrifugal force pushes the occupants outwards, simulating the effect of gravity. For example, a ring with a radius of 100 yards must rotate at a speed of approximately 3 revolutions per minute to create an artificial gravity of 1 g, similar to the one of the Earth. This design not only helps maintain physical health, but also provides a familiar environment that can alleviate the psychological challenges of living in space. The rotating habitats can include housing zones, recreational areas, and workspaces designed to optimize the use of the space and the available resources. Reliable and efficient food production systems are also needed to sustain populations for generations. Hydroponic and aeroponic systems offer solutions to cultivate without soil, using nutrient-rich water or mist to nourish the plants. These methods are very efficient, consume less water in the space than the traditional agriculture, and adapt well to the controlled environment of our ship. Hydroponic systems consist of cultivating plants in nutritive solutions with the roots suspended in water. Aeroponic systems, for their part, use a fine mist to supply nutrients directly to the roots. Both systems can cultivate a wide range of crops, from green leafy vegetables to tubers, providing balanced nutrition to the crew. These systems can be automated and supervised to maintain optimal growing conditions, ensuring a stable and reliable food supply. In addition, genetic modification and improvement will allow increasing the yield and nutritional value of crops. The efficient recycling of water and air is fundamental to the sustainability of a generation. Water recycling systems must recover and treat wastewater, ensuring a continuous supply of clean water for drinking, cooking, and watering. Advanced filtration and purification technologies, such as those used in the International Space Station, are already reaching high levels of efficiency in the ISS. For example, the water recovery system can recycle up to 98% of wastewater, like urine and sweat. This level of efficiency is necessary for long missions in which resupply from Earth is not possible. The ships of future generations will need to further improve this efficiency with the aim of achieving almost complete recycling to minimize the need for large water reserves. Air recycling is equally important and requires systems that remove carbon dioxide and replenish oxygen. Natural systems, such as photosynthesis in plants, can be integrated with artificial CO2 scrubbers to maintain a balanced atmosphere. Plants, in turn, not only provide oxygen, but contribute to the crew's psychological well-being by providing a connection with nature. Projects like Biosphere 2 have demonstrated the potential to create closed ecosystems in which plants, humans, and microorganisms coexist by recycling air, water, and nutrients. Although Biosphere 2 faced challenges, it demonstrated the viability of these systems and provided lessons for the design of life support systems in generational ships. The creation of a self-sufficient generational ship requires integrating advanced technology with natural processes to ensure the health and well-being of its inhabitants. Artificial gravity, efficient food production, and reliable disposal systems are the fundamental pillars of this design, which allow humanity to embark on a long journey to the stars and guarantee the success of a multi-generational mission goes beyond the physical and technological aspects of a ship, since it requires satisfying the mental, social, and educational needs of the crew, guaranteeing their health, motivation, and cohesion throughout the long journey. Isolation and confined spaces can significantly affect morale and mental health, and the lack of new stimuli and prolonged separation from Earth can lead to feelings of loneliness, anxiety, and depression. Addressing these issues is fundamental to maintaining a stable, motivated crew. Virtual reality technologies offer solutions for mental health and cultural connection by creating immersive simulations of terrestrial environments. Virtual reality, or VR, can provide a sense of escape and familiarity. Crew members will be able to see forests, oceans, and even social gatherings, which will help alleviate the feeling of isolation and maintain connection with their home planet. Artificial intelligence can also play a key role in supporting the mental health of the crew. AI therapists like Simon 2.0 from NASA can offer individual advice, monitor psychological well-being, and suggest strategies for coping with stress and interpersonal conflicts. These AI systems can adapt and learn from each generation, providing consistency in mental health support. Ensuring the intergenerational transfer of knowledge and skills is fundamental to the mission's sustainability. It is necessary to establish a comprehensive educational system that ensures each new generation receives the skills to operate and maintain the ship, as well as the knowledge to continue research and exploration. This should include formal education, practical training, and the preservation of cultural and historical knowledge. Embarking on an interstellar journey requires not only technological prowess, but also a deep commitment to the human spirit. By addressing the mental, social, and educational needs of the crew, we ensure the resilience and connection of each generation that carries the torch of exploration and survival. Advanced technology, such as virtual reality and artificial intelligence support, combined with solid cultural and social structures, will lay the foundation for a thriving community across generations. As we reach beyond our solar system, a harmonious blend of innovation and humanity will lead us to new worlds, securing our future as an interstellar species in a universe full of mysteries. One question rises above many others. Are we alone? This enigma, also known as the Fermi paradox, attempts to answer our understanding of the cosmos and our place in it. It is named after the physicist Enrico Fermi, who during an informal conversation at dinner reflected on the silence of the universe. The paradox confronts us with a marked contrast. On the one hand, the large number of stars, like grains of sand on Earth's beaches, suggests a high probability of extraterrestrial civilizations. On the other hand, our sky remains disturbingly silent, without any sign of these civilizations, despite advanced technology and the constant expansion of space. Not a single whisper or wave has reached us from the depths of space. This silence raises profound questions. What are the barriers that prevent potential civilizations from reaching or crossing the stellar expanse? Can the vast distances of the universe or the ephemeral nature of civilizations explain their absence? Or is the answer in the very structure of the appearance and survival of life in space, among a sea of stars? Our solar system offers a glimpse of the possibilities and limitations of life beyond Earth. The icy moons and distant worlds harbor oceans beneath their icy crust, reflecting the initial conditions in which life is believed to have originated on our planet. These hidden oceans, protected from the harshness of space, could be the cradle of life. However, it is very likely that these creatures are unable to travel beyond their icy borders or even be aware of such a possibility. Precisely this hypothesis has been raised recently, which forces us to rethink the variables of the Fermi paradox. Let's analyze in more detail to what extent it affects the answer to why we have not yet been able to hear the echoes of alien civilizations in the universe. The silence that reigns in space is an enigma that has puzzled minds for decades. Let's imagine a universe in which technological wonders and interstellar communications fill the void between the stars. Such are the expectations of our science fiction and the logical predictions based on the Drake equation, which estimates the number of active, sociable extraterrestrial civilizations in the Milky Way. However, when we delve into the immensity of space, the reality is surprisingly different. The awaited intergalactic speech remains only an expectation. The Fermi paradox poses an apparently simple question. There are billions of stars in the galaxy, many of which have planets similar to Earth. But where is everyone? This fact has undoubtedly caused perplexity among scientists and the public in general, which has given rise to numerous theories that try to solve this mystery. A common explanation is the theory of the Great Filter, which suggests that at some point in the evolution of a planet to an intelligent life capable of colonizing galaxies, there is a highly improbable step that few civilizations, if any, overcome. On the other hand, the hypothesis of a zoo suggests that advanced extraterrestrial beings deliberately avoid contact with us to allow natural evolution and sociocultural development, just as the caretakers of a zoo observe the animals in a sanctuary. Interestingly, despite our sophisticated antennas and listening devices, we still have not captured the slightest whisper from space. This leads us to speculate that perhaps our listening techniques are not adapted to alien communication methods. Worse still, intelligent life is extremely rare or short-lived due to self-destruction or cosmic events. Especially given the vastness of space that we have already scanned, it is difficult to draw other conclusions. Why is this happening? It could suggest that our knowledge is incomplete or that we're listening incorrectly and at the wrong time. However, perhaps things are simpler than they seem. A recent and intriguing proposal is the fishbowl world hypothesis. The traditional search for extraterrestrial life often focuses on Earth-like planets in the habitable zones of their stars, with liquid water and an atmosphere capable of sustaining life as we know it. However, this vision may be too limited and not account for life that does not conform to our terrestrial expectations. The fishbowl world hypothesis proposes a radical change in the search for life. According to it, life thrives in underground oceans completely surrounded by a thick layer of ice. These worlds offer a stable environment protected from cosmic dangers, such as radiation and meteorite impacts, which favors the development and evolution of complex ecosystems in isolation. This theory is inspired by the work of scientists such as Alan Stern, whose contributions to space exploration have shed light on the mysteries of the icy celestial bodies in our solar system. For example, the New Horizons mission discovered intriguing characteristics on Pluto and its moon Charon that suggest the presence of underground oceans, as well as the possibility of similar conditions even in the coldest regions of the Kuiper Belt. In our solar system, moons like Enceladus and Europa, which orbit Saturn and Jupiter respectively, have geysers that expel water vapor and ice particles into space, observed by instruments like Cassini, which point to a dynamic and active environment under their icy crust. But how do these icy planets and dwarf planets affect the fishbowl world theory? Well, the key is in understanding the complex interaction of gravitational forces, radioactive decay, and perhaps even hydrothermal vents at the bottom of the ocean, all of which can contribute to the creation and maintenance of underground oceans in such an environment. Life as we know it, or even life forms beyond our current understanding, could find a way to thrive, isolated but protected from the harshness of space by a thick layer of ice. In these isolated ecosystems, life could thrive without the ability to contemplate the stars or the universe beyond its cold confines. This raises the question, how could these isolated creatures communicate or even imagine a reality beyond their own? This fact is disconcerting, since it breaks our preconceived ideas about what an advanced civilization could be like. On this basis, we can assume that the universe could be full of life hidden in these natural refuges. Perhaps our galaxy is full of these quiet and isolated worlds whose inhabitants unknowingly share the cosmos with us under the ice layer of a distant world. The concept of communication acquires a new dimension far removed from our earthly perceptions. In these hidden oceans, life forms can develop unique communication methods deeply influenced by their isolated environments. On our planet, the oceanic depths allow us to glimpse how life can adapt to the perpetual darkness of the subsoil. Marine species, such as whales and dolphins, use sound to communicate over long distances up to several thousand kilometers, a method that is efficient and effective in the dense aquatic environment. This terrestrial analogy suggests that the creatures of the hidden oceans of the icy worlds may also depend on sound or other forms of non-visual communication, negating the need for technology such as radio signals. In the absence of light, these creatures could have developed advanced echolocation capabilities similar to those of living beings on Earth, allowing them to see through sound. The acquisition of knowledge in this context would be fundamentally different, potentially focusing on nuanced acoustic information rather than visual or electromagnetic signals. It is possible that these mysterious beings that thrive in their isolated worlds have a deep knowledge of their environment, but remain unaware of the cosmos that surrounds them. However, the vast universe, with its countless worlds, not only offers opportunities for life, but also formidable challenges for civilizations seeking to reach the stars. Among these challenges, the gravity of the planets in the solar system is a colossal barrier to the dream of interstellar exploration. This introduces another critical factor in the Drake equation, known as the exoplanetary escape factor, which assesses the feasibility of space travel from worlds other than our own. The exoplanetary escape factor is an important addition to the Drake equation, as it offers a method to quantify the difficulties that an extraterrestrial civilization might face when trying to escape the gravitational pull of its home planet. The escape velocity equation of a planetary object shows that larger and more massive planets pose an enormous problem. The Earth, whose escape velocity is 1,119 kilometers per second, serves as a reference for comparison. For example, a hypothetical super-Earth with a mass much greater than ours would have a prohibitively high escape velocity, making conventional space travel an insurmountable task. Let us imagine the scale of engineering and energy necessary to separate from a planet much greater in size and mass than Earth. The escape velocity of those worlds would be much greater, requiring propulsion systems far superior to our current capabilities. Those worlds could be rich in life and even have advanced civilizations, but they would still be eternally isolated and their skies eternally out of reach. These civilizations could develop alternative routes in the confines of their own world, but their technological advances would be limited to the confines of their own world. However, it is conceivable that these civilizations could explore alternative routes in worlds with an isolated environment and their skies eternally out of reach. These civilizations could develop in complete ignorance of the cosmos and with technological advances limited to the confines of their world alone. However, it is conceivable that these civilizations could explore alternative paths in space. Innovations such as space elevators, orbital rings, or even harnessing the energy of planetary rotation could provide solutions to the difficult problem of achieving high speeds. However, these technological advances will require materials and energy sources far beyond what we currently deem possible. Furthermore, it would further complicate the view about the development of life on icy moons and dwarf planets locked under a thick layer of ice. These worlds provide protection and stable conditions for life, but also create additional layers of insulation for intelligent beings in such environments. The very concept of space may be incomprehensible, hidden behind impenetrable barriers of ice and rock. This raises the question of how these creatures would perceive their place in the universe and what colossal effort it would take for them to break the ice ceiling and venture into the unknown. It would be logical to assume that, in the heart of a world bound by the heavy chains of gravity or by a dense layer, the rhythm of life and the trajectory of civilization follow a less-known path. Here, the attention of intelligent life forms would visibly turn inward toward their own world. In such societies, environmental limitations could lead them to focus on mastering their immediate environment, optimizing their habitat, and deeply exploring their world. In such a case, there is nothing strange about their lack of connectivity. Being unable to go beyond their planet is necessary for the concept of space to be a foreign idea, both figuratively and literally. Now, as we stand on the threshold of a new era in space exploration, our eyes are turning not only to the distant stars, but also to the icy guardians of our solar system. Several ambitious missions will head to this icy expanse in the coming years. The Europa Clipper, whose launch is scheduled for October this year, aims at Jupiter's moon Europa. The Dragonfly, whose departure is scheduled for 2028 destined for Titan, and several proposed conceptual missions target Saturn's moon, Enceladus. These celestial bodies, once considered icy wastelands, are now seen as prime candidates in the search for extraterrestrial life in our solar system. These missions are equipped with advanced technology to penetrate the ice layers and explore the vast oceans beneath. By analyzing the composition of the columns of water expelled into space, studying the geology of the ice, and mapping the underground oceans, scientists hope to find signs of life or, at least, the conditions necessary for its existence. In any case, so far there is no direct evidence of extraterrestrial life in our system. However, in the next decade, this veil will lift and shed new light on this issue. The data collected may provide empirical support for the idea that life can exist in conditions very different from those on Earth, and that the universe may be teeming with unseen life, much of it hidden in isolated worlds like fishbowls. However, if we find nothing, we may have to discard the idea and start looking for clues elsewhere. One thing is clear. Our search, whether it uncovers vibrant alien ecosystems or absolute voids, will forever change our cosmic perspective and propel us into the next chapter of human discovery. Saturn has captivated the human imagination from ancient civilizations to modern astronomers. The Maori of New Zealand, separated by vast oceans and without telescopes, somehow knew that Saturn had rings. Thus the mystery deepens. Saturn has long been a symbol of the unknown and the mysterious. Its iconic rings have been the subject of awe and speculation since the time of Galileo. But what if we told you that these rings, as eternal as they seem, are actually an ephemeral cosmic phenomenon? Adding to the intrigue is a storm twice as wide as Earth, with a mysterious hexagonal shape that lashes Saturn's North Pole. What forces could have created such a geometrically perfect formation? But the mysteries do not stop there. The moons, Titan and Enceladus, offer conditions that could harbor life. Lakes of liquid methane and geysers that launch water and organic matter into space make these satellites more than just celestial bodies. They're potential homes for life. Join us as we take a closer look at this enigmatic giant and its cosmic mysteries. Our journey begins with Galileo Galilei, the Italian astronomer who pointed his telescope at Saturn for the first time in 1610. What he saw left him perplexed, a planet with something like ears. He did not realize that he was seeing the edges of Saturn's magnificent rings, a feature that would baffle astronomers for centuries. Galileo's telescope was primitive by today's standards, and the true nature of Saturn's ears remained a mystery. It was not until 1655 when Christian Huygens, armed with a more advanced telescope, correctly identified them as a system of rings surrounding the planet. Entering the modern era, we witnessed the Pioneer 11 mission, the first spacecraft to fly by Saturn in 1979. This mission provided us with the first close-up images of the planet and its rings, revealing intricate details that were previously inaccessible to terrestrial telescopes. But it was the Cassini mission that truly revealed Saturn in all its splendor. Launched in 1997 and arriving at Saturn in 2004, Cassini spent 13 years studying the planet, its rings, and its satellites, from the discovery of columns of water ice on Enceladus to capturing the ethereal beauty of a hexagonal storm at Saturn's North Pole. Cassini revolutionized our understanding of this distant world, and here is an interesting fact. Long before the arrival of telescopes, the Maori of New Zealand had myths that described Saturn with a pararo, or belt, around it. How they knew this remains a matter of debate and speculation. But, as we will see later, Saturn hides more than one mystery. What do you think could have created a hexagonal storm with an area larger than Earth itself? Saturn is home to a geometric enigma at its North Pole, a six-sided storm that has baffled scientists for decades. This six-sided wonder isn't just a superficial characteristic, but a deep and lasting mystery that defies the foundations of fluid dynamics and planetary atmospheres. The hexagon was first discovered in 1981 by the Voyager spacecraft, but it was not until the Cassini mission, which orbited Saturn between 2004 and 2017, that we were able to see this cosmic spectacle in the front row. The high-resolution images from Cassini showed a symmetrical jet stream surrounding the hurricane-like vortex at the center of the hexagon. Unlike the chaotic weather systems of Earth, Saturn's hexagon is a marvel of geometric precision. So, what causes this hexagonal storm? Researchers at Harvard University have developed a 3D model suggesting that deep thermal convection in Saturn's outer layers may be responsible. This model shows that the storm could extend thousands of kilometers into the depths of Saturn's atmosphere, far beyond what we can see. Interestingly, scientists have been able to reproduce the hexagonal pattern in a lab. Although these experiments don't capture all the nuances of Saturn's complex atmosphere, they offer a glimpse of extraterrestrial phenomena. Saturn's hexagonal vortex contrasts sharply with Earth's polar vortex, which is irregular and less stable. This difference raises questions about the fundamental properties that distinguish the atmospheres of gas giants from those of terrestrial planets. The longevity of the hexagon is another mystery, as it has been observed for at least 4 decades, and possibly much longer. This constant characteristic suggests that whatever feeds the hexagon is not a temporary phenomenon, but a stable, perhaps permanent, aspect of Saturn's internal dynamics. Let us now turn our attention from the mystery of the hexagon to another wonder of Saturn. Its rings are more than just a celestial jewel. They are dynamic, ever-changing systems that intrigue both astronomers and the public. But what are these rings made of, and why are they so ephemeral? Saturn's rings are mainly composed of water ice, with a mixture of dust and rocky material. Their size varies from tiny particles to huge chunks the size of houses. These ice particles are not static, but are in constant motion under the influence of Saturn's gravity and the gravitational attraction of its satellites. The rings are divided into several divisions and gaps, each with its own unique characteristics. The most notable are rings A, B, and C, separated by gaps such as the Cassini division, a 3,000-mile gap between rings A and B. The origin of Saturn's rings has been a subject of debate. One popular theory suggests that they form from the remains of a shattered moon. Another theory claims that they are the remains of material from the formation of the solar system, captured by Saturn's gravitational force. Recent research has also shown that the rings may be much younger than Saturn itself, perhaps around 400 million years old, based on a rate of dust contamination. Saturn's rings do not last forever, but are slowly disappearing due to a phenomenon known as ring rain, in which particles from the rings are drawn into Saturn's atmosphere. This process is accelerated by the bombardment of micrometeorites and interaction with Saturn's magnetic field. At the current rate, some scientists predict that Saturn's rings could vanish in 100 million years. The depletion of the rings would not only change the appearance of Saturn, but could also have consequences for it in 100 million years. The depletion of the rings would not only change the appearance of Saturn, but could also have consequences for its atmosphere and magnetic field. For a moment, we realize that even the most fascinating features of our universe are not immune to the inexorable forces of physics, destined to disappear in the annals of eternity. Saturn, the ring giant of our solar system, is not only a celestial wonder, but also a cosmic playground containing some of the most intriguing satellites, two of which, Titan and Enceladus, have fascinated scientists and sparked debate about the possibility of life beyond Earth. Titan is a world shrouded in mystery. Its dense atmosphere is rich in organic compounds, and there are lakes and rivers of liquid methane on the surface. But what is truly surprising is the rate at which Titan is moving away from Saturn 100 times faster than previously thought, which is an astonishing 43 centimeters per year. This rapid drift suggests a dynamic and evolving relationship between Titan and Saturn. Could this drift affect Titan's internal dynamics and perhaps even its potential for life? An atmosphere rich in organic compounds such as nitrogen and methane and the possibility of an underground ocean make Titan a tempting target in the search for extraterrestrial life. But the question remains, what would life be like in an environment so radically different from Earth's? And let's remember Enceladus, another Saturnian satellite very different from Titan. It is an icy world with a highly reflective surface that outshines any other body in the solar system. Enceladus takes the concept of an ocean world to a new level. Not only does it have an underground ocean, but it also expels it into space, where a space probe can gather samples. This ocean contains most of the chemical ingredients necessary for life, including hot, mineral-rich water gushing from hydrothermal vents. Hydrothermal vents can provide the conditions needed for life as we know it. On Earth, these sources teem with life forms that thrive in extreme conditions. Could Enceladus' vents harbor similar but alien life forms? Enceladus also contributes to Saturn's E-ring, a unique feature that further enriches the dynamic relationship between the Moon and its host planet. The icy particles of this ring offer a window into the Moon's internal chemistry, providing clues that could reveal its secrets. Titan and Enceladus are two moons orbiting the same planet, but with very different characteristics. Both present compelling arguments for the possibility of life, fueling our curiosity as we ponder the possibilities of life on Saturn's moons. It should be noted that our curiosity is not limited to telescopes and computer models. Upcoming missions aim to study these satellites up close and perhaps answer some of our most pressing questions. Meet Dragonfly, NASA's ambitious mission to Titan, scheduled for launch in the 2030s. This helicopter will fly across the very terrain of Titan, from the dunes to impact craters. The main objective of Dragonfly is to search for life's basic components. It will analyze complex organic compounds in the atmosphere and on the surface, providing key data on Titan's chemistry. Equipped with a set of scientific instruments, Dragonfly seeks to understand the geological processes of the moon and how they relate to its potential for life. Could Titan's unique chemical composition and liquid methane cycles offer a different recipe for life? Although there are no missions planned to Enceladus currently, it has become an ideal candidate for future explorations. Scientists are proposing missions that could fly through Enceladus plumes and take samples directly from its ocean underground. Such a mission could analyze the plume's chemistry in search of signs of life or prebiotic chemistry. The presence of hydrothermal vents in the oceans adds another layer of intrigue, suggesting an environment in which life could thrive despite the technical challenges. A mission to Enceladus could revolutionize our understanding of life's potential in the solar system. It could provide direct evidence of extraterrestrial life, or at least clues about the conditions necessary for life to exist. Music, as we mentioned earlier. The rings of Saturn do not last forever, as was once thought. Recent studies have shown that a process that can last hundreds of millions of years is causing these icy wonders to slowly fade. But how important is this for Saturn and its complex atmospheric dynamics? According to a study by the Japan Aerospace Exploration Agency, this material, composed mainly of water, causes a decrease in the electron density in the atmosphere of Saturn. This phenomenon, known as ring rain, significantly affects Saturn's atmospheric conditions. The ring rain is not just a trickle, but a torrent that drags water in amounts equal to an Olympic swimming pool every half hour. The mystery is compounded by the relative youth of Saturn's rings. Although Saturn is about 46 billion years old, data from NASA's Cassini mission suggests that the rings could be only a few 100 million years old. This leads us to wonder if the rings of Saturn are so young. What catastrophic event could have led to their formation? Was it the destruction of a moon, or perhaps the capture of a passing comet? Cassini's Space Dust Analyzer has added another layer of complexity. For 13 years, it collected 163 dust particles that came from outside the Saturn system. Surprisingly, the rings turned out to be quite clean, suggesting that they have not existed long enough to accumulate excess cosmic dust. This cleanliness raises the question that, if the rings are young, why have they not collected more cosmic dust? The absence of cosmic dust in the rings challenges our understanding of their age and interaction with the broader cosmic environment. It is as if the rings were in a cosmic laboratory or in a clean room, isolated from the dust that permeates the rest of the solar system. As the rings are depleted, Saturn's appearance will undergo a dramatic transformation. These rings have been the hallmark of the planet, and their disappearance would not only change the appearance of Saturn, but could also have unknown consequences for its atmosphere, even affecting the planet's albedo and heat retention. The loss of the rings could have a ripple effect on Saturn's atmosphere, altering wind patterns and even affecting the planet's iconic storms. The full extent of these changes is still unknown, making it a topic of great scientific interest. Interestingly, the fate of Saturn's rings could be inextricably linked to that of its satellites. Some theories suggest that gravitational instability could have destroyed some of the icy satellites orbiting Saturn, providing enough material to form the rings. The rings and satellites of Saturn are like companions in a cosmic dance, each affecting the other in subtle but significant ways. As we continue to study these celestial bodies, we can state without a doubt the rings and satellites of Saturn are like companions in a cosmic dance, each affecting the other in subtle but significant ways. As we continue to study these celestial bodies, we can state without a doubt that the fate of one can shed light on the other's mysteries. Humanity stands on the threshold of a new era, defined not only by exploration, but also by the bold dream of colonization. For decades, our gaze has been fixed on the familiar: the moon, our celestial neighbor, and Mars, the red beacon in our night sky. These worlds, once the subject of science fiction, now beckon us with the promise of new frontiers. But beyond these well-traveled paths lies a world shrouded in mystery, one that is changing our understanding of what it means to be a moon. This is Titan, Saturn's largest satellite. Titan is a world covered by a dense atmosphere, something unusual for a moon. It is a place where rivers and lakes flow, but not of water, but of liquid methane and ethane. Here it rains gasoline, and the cold is more intense than anything that can be experienced on Earth. However, in this alien landscape lies the potential for something extraordinary. Could Titan, a world so different from our own, be the key to our future in space? Could this distant moon hold the secrets not only to survive, but to thrive beyond our planet? It is a small step for man. Applause. As we turn the pages of our history of space exploration, the moon and Mars become beacons of human ambition. The moon, our closest celestial neighbor, has always been a constant companion in our night sky, a symbol of our desire to abandon the planet's confines. Mars, in turn, with its striking resemblance to Earth, fuels our dreams of finding a new home in space. However, the moon, despite its proximity, presents significant problems. Its surface is arid and a desert, devoid of atmosphere and without protection against the harshness of space. The lunar environment is a vacuum that exposes astronauts to extreme temperatures and cosmic radiation. The absence of atmosphere means that there is no air to breathe, no wind to carry sound, no sky to protect from the constant bombardment of solar and cosmic rays. Mars, although more similar to Earth, is not without problems. Its atmosphere, composed mainly of carbon dioxide, offers little protection against solar and cosmic radiation. The Martian environment is inhospitable, and the temperatures at the poles can descend to minus 27 degrees Fahrenheit. The lack of a global magnetic field exposes the surface to the full force of the solar wind and cosmic rays. In contrast, Titan, the largest satellite of Saturn, presents a very different environment, wrapped in a dense atmosphere. Titan offers a natural barrier against the dangers of cosmic radiation. This atmosphere, richer in nitrogen than that of the Earth, is key to protecting future colonists from the cosmic rays that bombard less protected worlds like the Moon and Mars. The atmosphere of Titan is not only a shield, but a door to opportunities. Unlike the Moon and Mars, the atmosphere pressure on Titan's surface is 15 times greater than on Earth, creating a pressure environment surprisingly familiar to human explorers. This dense atmosphere opens new possibilities for exploration and colonization, possibilities that are beyond the reach of our most ambitious space objectives. As we rethink our objectives for space colonization, Titan becomes an attractive alternative, a world in which the atmospheric and radiation problems that limit our ambitions on the Moon and Mars become strengths. Titan invites us to imagine a future in which humanity can thrive under the protective embrace of an alien sky, a future in which the mysteries of this distant moon become stepping stones for our expansion into space. As we mentioned previously, Titan, a moon full of mysteries, orbits Saturn and was discovered in 1655 by the Dutch astronomer Christian Hens. Titan has captivated the imagination of scientists, artists, and dreamers since then. This world is both similar to and very different from our Earth. The environment of Titan is unlike anything else found in our solar system. It is the only known moon with a dense atmosphere and the second largest moon in our solar system after Ganymede, a satellite of Jupiter. But it is not only its size that makes Titan stand out, but the rich composition of its atmosphere and surface, which truly differentiate it. This moon is surrounded by a thick atmosphere rich in nitrogen, similar in composition to that of the Earth, but much denser and more extensive. It is impregnated with organic molecules that create a diffuse orange glow that obscures the surface of the satellite. This nitrogen-dominated atmosphere provides protection against solar radiation, which contrasts strongly with the arid sky of the Moon and Mars. Under this alien sky is a landscape that is both familiar and utterly strange. The surface of Titan is formed by rivers and lakes, but they are not masses of water as we know them, but are filled with liquid methane and ethane that flow through channels excavated in the Moon's icy crust. These seas of hydrocarbons are a true wonder, a testament to the diversity of the universe. The presence of these fluids on the surface is a key characteristic that distinguishes Titan from other celestial bodies. The water cycle shapes the climate and geography of Earth. In Titan, a similar cycle occurs, but the role of water is played by methane and ethane. This hydrocarbon cycle, with methane rains and ethane lakes, creates a dynamic environment that can provide clues to understanding the complexity of planetary atmospheres. Thus, by breaking the limits of our usual perception, we're gradually discovering what exactly makes a planet or moon habitable. Its nitrogen-rich atmosphere and surface fluids open the door to new possibilities. Let's discover what they are. The moon's nitrogen-rich atmosphere provides a natural barrier against cosmic radiation, one of the main challenges for space colonization. Why do we pay so much attention to solar radiation? The answer is simple, but deeply important. Solar radiation is a relentless destroyer of living cells. It does not only affect microscopic life forms, but directly affects us, human beings. Unprotected exposure to solar radiation can cause serious cellular damage that destroys the very structure of our biological existence in space. By spreading uncontrollably, this radiation poses one of the greatest threats to the survival and health of astronauts. It is the atmosphere and the magnetic field that protect us on Earth. It is the dense nitrogen atmosphere that provides vital protection, making it a safer haven for future human colonists than the arid landscapes of the Moon or Mars. Under this protective dome lies a world of liquid methane and ethane. These lakes and rivers of hydrocarbons contrast radically with the bodies of water that we know on Earth, but offer intriguing possibilities. Let's imagine a world in which ships sail through seas of methane, where the familiar concept of the water cycle takes on a completely new form. The presence of these fluids on the surface is not just a curiosity, it is a resource. Methane and ethane have the potential to be used as fuel, providing energy for future colonies. This abundance of hydrocarbons makes Titan an attractive target for colonization, offering a solution to one of the biggest problems of space habitability, sustainable energy. But the gifts of Titan do not end here. Under its icy surface lies another treasure, water ice. Water, essential for human life, is abundant on the satellite trapped in its icy crust. The presence of water ice and hydrocarbons turns this moon into a deposit of vital resources, laying the foundation for a self-sufficient human presence far from Earth. Titan, a world of incalculable potential, also presents immense challenges. The extreme cold, with temperatures dropping to minus 356 degrees Fahrenheit, creates an environment inadequate for human life as we know it. In turn, the methane rain, a unique phenomenon on this moon, adds another layer of complexity to the survival equation. To overcome these challenges, we must resort to the height of human ingenuity. The colonization of Titan will require not only adaptation, but a complete rethinking of human habitability in extreme conditions. Let's imagine homes designed to withstand low temperatures, insulated with materials yet to be invented, and that take advantage of the energy of Titan's own resources to provide heat and comfort. These habitats could be equipped with systems to convert atmospheric methane into heat, turning the problem into a resource to solve it. But survival is more than just staying warm. The methane rain, although an obstacle, could become an advantage. Advanced collection and filtration systems could recycle methane not only as an energy source, but also as raw material for essential products. Let's imagine a human colony on Titan. Let's imagine domed cities with an architecture that combines science and art, designed to harmonize with Titan's unique environment. These structures, resistant to the cold and methane rains, would be interconnected, forming a network that would demonstrate human resilience in the face of alien conditions. Inside these domes, life would flourish. Hydroponic gardens would provide food, recycling systems would conserve resources, and public areas would foster a sense of community. It is a place where humanity has not only survived, but flourished, decisively adapting to Titan's challenges. Colonizing Titan is not just some distant dream. It is a future that invites us to accept the challenge. With each technological advance, with each bold leap of imagination, we get closer to making this alien world a new home for humanity. When observing the prosperous human colony on Titan, it is clear that this moon is more than just a new home for humanity. It is a center of economic and scientific opportunities. Its unique environment and abundant resources offer unprecedented prospects. The economic benefits of colonizing Titan stem from its vast hydrocarbon reserves. The key components of Titan's lakes and atmosphere are potential sources of energy and valuable raw materials for chemical synthesis. The ability to harness these resources could turn Titan into an economic hub that meets the colony's needs and potentially supplies materials for interplanetary trade. From a scientific point of view, Titan is a gold mine. Its complex atmosphere and surface chemistry offer unique research opportunities that allow a better understanding of organic chemistry and astrobiology. The study of Titan's methane cycle and its prebiotic chemistry could reveal secrets of the origin of life, not only on Earth, but potentially throughout the cosmos. In addition, Titan's position in the solar system and its resources make it an ideal launch pad for future space explorations. Its low gravity and abundant fuel reserves could facilitate the launch of spacecraft to distant destinations, making Titan a strategic outpost for exploring the outer solar system and beyond. However, these opportunities bring important ethical considerations. As we embark on the colonization of Titan, we must reflect on our responsibilities when interacting with this new world. The conservation of Titan's environment, respect for its unique characteristics, and careful management are fundamental. We must approach Titan not as conquerors, but as its custodians. The way we relate to this world will reflect our values and our ability to balance progress and responsibility. As we conclude our journey, let's reflect on the key points. A moon once shrouded in mystery has turned out to be a world full of potential. We have explored the protective properties of Titan's nitrogen-rich atmosphere, a natural shield against the dangers of cosmic radiation. We have traveled through alien landscapes where rivers and lakes of methane and ethane cross icy terrains, offering resources that could secure our future in space. Our journey has also led us to the potential of a vibrant human habitat where ingenuity and resilience have turned challenges into opportunities. We saw how Titan's economy, driven by its abundant resources, can be the cornerstone of our interplanetary efforts. As we reflect on the future of humanity on Titan, we remember that colonization is not just about achieving technological perfection, but a journey that forces us to grow, learn, and respect the universe in which we live. So we leave you with a big question. What does this step mean for the future of humanity? How will our efforts on this distant moon affect our destiny in the vast, unexplored expanse of space?